And as all of you are here, the gradient flows have become a lot of like a unifying theme for a lot of algorithms we keep using in computational statistics. There was a saying, meme I like everything that works because it's Bayesian. Now I think everything that works because it's probably a gradient flow, right? It's including the Bayesian base update. So yeah, hopefully we'll have a very nice set of speakers today that I hope you will enjoy, right? So I will just do some housekeeping. So there's no file safety alarm expected. So if you hear one, you have to leave. And there's a tree over there, just in the corner, which is the 5 meeting point. So for online people who are online right now, we will ask you to mute. So you should ask any questions in the chat, and we will be reading the chat. And if we have time at the end of any talk for online questions, we will take them. There will be coffee. The coffee will be upstairs. So you will leave here and go upstairs. And then finally, the talks will be recorded. And any questions you ask may be recorded. Be unfriendly. Okay, Nick. So it's my great pleasure to know the first speaker is Nick. He has done his PhD at Imperial, and now he is at King's College as well. His talk will be about what we'll talk about.
Okay. Yeah, thank you so much for inviting me. It's really a great pleasure to be here. And yeah, personally, really looking forward to all the talks. Been, very interested in all these different topics. And today I'd like to present something which is maybe a little bit different from gradient flows per se, but sort of inspired by them. And it wouldn't have been possible with the amazing collaborators, Francisco, Shreyas, and Dennis. So these are PhD students from Cambridge, and Dennis is a PhD student in Karlsruhe. And so, okay, we are going to discuss the sampling problem. So we are going to try and sample from the target measure pi, which is given in this form. And the important ingredient is the potential V. And there's the normalizing constant. So we're going to assume that V and gradients of V are tractable to evaluate computationally. Okay? And then the standard task is to produce samples from pi. And a standard approach would be to use overdamped Langevin dynamics given by an SDE of this form. And the key observation is, of course, if we start with an arbitrary distribution for y0 and we let the dynamics run for long enough, then as t goes to infinity, we will recover in law the distribution pi, where the relationship between pi and v, remember, is given as above. Okay, so the nabla v is minus gradient of log pi, and importantly, we don't need access to the normalizing constant z. Basically, you should think about it as follows: that maybe v defines valley in which the particle moves around, like this. So these would be equipotential lines of the potential. And then the particle trajectory fills up the space in such a way that long-time ergodic averages represent averages against phi. This is a picture that I decided to include to start off the workshop, because if you think of the distribution of the law of y as a point in an infinite dimensional manifold, so think of the set of probability densities as an infinite dimensional manifold, heuristically, like this oval shape over here, then we can think of the evolution of this object as a point in the space. And it has been famously observed by Jordan Kinderlehrer and Otto in the 90s that the evolution of this object can be understood as gradient flow dynamics on this valley defined by the relative entropy towards the target pi. Okay, but this does not play such a big role actually in this talk. So I'm going to discuss something a little bit different, but related. So we can also think about, so we can do a different kind of approach, namely, I go back one step. Here, this curve of distributions that converges in the long time limit towards the target pi is given in some sense implicitly by this gradient flow dynamics. But a different approach would be to manually fix the curve pi t from the start so that the final distribution pi 1 agrees with the target, and pi 0 would be some sort of tractable distribution. For example, a Gaussian that we can use to produce samples easily. Okay, there's different ways of doing this, but this is maybe the most popular way of constructing this. There's the prior, we've got the negative log likelihood h, and then if t is equal to 0, we recover the prior pi 0, and if t is equal to 1, we get the posterior. And so this is going to be an interpolating curve of distributions that we can try to track algorithmically. Okay, so you can see here, maybe the prior is this red curve. It's thinking of this artificial computational time as temperature, you might think of this distribution as hot, and then the posterior becomes cold at t equals to 1. So that would be, in physical terms, an inverse temperature. And often it's the case that the red curve, or in this case the prior, is much easier or in fact straightforward to sample from. Okay. Now what can we do with this? And this is a sort of standard idea, which is sometimes called annealing or tempering, and it's also sort of one of the main background ideas in sequential Monte Carlo, SMC. And now the idea is to reproduce this curve of distributions using an SDE like this. And you see it looks quite similar to the SDE that we had before, only that we've added this control term. And note that now this potential depends on t. So before we didn't have this, and the potential was a fixed potential that is derived from the target pi. Now, this is a time-varying potential. We've got one potential, which is induced by the interpolation. And so there's a potential for every curve in this interpolating family. Why is it good to look at it like this? You see, we can think of this as being locally at equilibrium. So we can think if this control phi is 0, and we start the dynamics in pi 0. And also this dynamics will remain, the law of yt will remain pi 0, equal to pi 0 for all times, because pi 0 is invariant for the dynamics when t is 0 again. Okay. So you can think of this as, without this phi, this SDE keeps the distribution in equilibrium. And then if we want to make a move from the red to the violet curve, for example, we need to, first of all, change the potential V. So we change the T here, but this will not be enough to organize the transition, but we also need to apply this control phi to do this. Okay. And so imagine we found such a time-dependent vector field phi t. Then this would solve the Bayesian sampling problem, because we could just start with samples from pi 0, which by construction are simple to obtain, and then we simulate this dynamics using the control nabla phi t and get samples at pi 1, at time t equals to 1 from pi 1. And this holds the promise of somehow modifying gradient flows in an interesting way, because the convergence towards the target pi happens in finite time, right? So in this other setting, we had to wait until time goes to infinity, whilst with this idea, we just wait until time t equals to 1. At least that's one of the selling points of this approach. Yeah, okay. The challenge, of course, now is to find this control vector field phi, or nabla phi t. And the rest of the talk is going to be about an approach, how to do it. Maybe other questions until here?
The questions at the end.
Okay, questions at the end. Okay. Let's do it like this. Okay, so this talk in general, I'm going to talk a little bit. It's heavily influenced from the recent rise of diffusion models, which, broadly speaking, solve a problem like this. There's two marginal distributions here in this picture denoted by rho 0 and rho 1. And we want to find a diffusion that starts in rho 0, and then following this diffusion, we get to rho 1. So there have been lots of works on this in different settings, and it has produced outstanding and incredibly good results for these generative modeling tasks, where the idea is to generate images from previously seen images on the internet, like this. Okay, this is a different application. So here's not sampling, it's generative modeling. But in this talk, we show how these ideas can be applied to the sampling task. Okay. This slide and the next one are going to be a little overview of the idea, and then we are going to go into details in the rest of the talk. Okay, so there are two steps, and the first step is to think of the problem as, so maybe here we want to find the diffusion that goes from rho 0 to rho 1. But the first step consists in thinking about two diffusions, one that goes forward from here to here, and the other one that goes backwards. So this is the first one, this is the second one, and the first one goes forward like this, and the second one goes backward like this. And they can be described by forward and reverse time stochastic differential equations of this form. I can discuss some of the stochastic analysis behind it, which is mainly related to the integration here, but I think I can do this in the break. The most important bit is that there are two vector fields involved. So this blue one, this red one, that steer the diffusion in a certain way, and there are two initial or final distributions involved, pi 0 and pi 1, which initialize the forward or the backward diffusion. Okay, so that's pi 0, that's pi 1. Then there are these vector fields that drive the diffusions either forward or backwards. Okay. So instead of one diffusion that goes from one measure to the other measure, we do two diffusions, one forward and one backward. And the idea is that we try to match the corresponding probabilities on path space. So by these stochastic differential equations, they will induce probability measures on path space. So every path gets a certain probability, roughly speaking, assigned to it, according to the initial condition and the vector field. And so think about it like this. These two, the blue and the red path measure, are defined in different ways, but they are objects that live in the same mathematical space, and so we can ask them to be the same. And so if they are the same, like here, then although the two diffusions are described in different ways, they are in the end the same. And by this construction principle, we ensure that the one diffusion, which is equal to both the forward and the backward diffusion, respects both the initial and the final time marginal. Okay, so this is the main idea in step one. Yeah, so we make sure that the induced path measures coincide, and this is the main idea for ensuring the transport property, okay, from pi 0 to pi 1. Okay, step 2 is the solutions to the step 1 will not be unique, so we can find forward and backward diffusions that agree in terms of their induced path measures, but there's no uniqueness in this construction because, for example, if you see in these two pictures and also this picture, there is an infinite number of diffusions that can, of course, connect one distribution to the other one, and just using the idea from step 1 will not prevent this. And so in the upcoming slides, I will, so when we discuss step 2, we will discuss a little bit how to resolve this non-uniqueness. It's not really strictly necessary to resolve this, because if we're really only interested from sampling from pi 1, then any of those diffusions will do an okay job. But if we have so much non-uniqueness in the pipeline, this will lead to numerical instabilities and also to weak interpretability of the output of the algorithm. Okay, and so finally, I didn't put this here, but sort of constraining further the possible solutions to this framework will then lead to connection between the vector fields A, B, and the control drift nabla phi. Okay. Yeah, so this is the general outline. Now we are going to go a little bit more into technical details. So first of all, the diffusions, just repeat them here. This is just notation. This is just meant to show that writing these SDEs in this way, we can have, so the vector field B and the terminal condition pi 1, this induces a path measure, and this is notation. So the path measure is going to be denoted P, and then with this backward arrow, because it's the path measure that is induced by the backward diffusion, with terminal condition pi 1 and vector field B. And likewise, the forward one is denoted in this way, with a similar notation, but with the arrow going in the other way. And if you're not familiar with these SDEs, it might help to think of these Markov chains. So literally, we can define update steps in this way, where delta is the step size. Then as delta goes to 0, we will cover, in a certain sense, these SDEs. Okay. And then the framework, which is related, so which implements step 1, is, remember, we want these path measures to be the same. So we want these paths to overlap, like in the picture. So that means we want this to be the same as this. These are two probability distributions. We can do this by fixing a divergence, by choosing a divergence. So this might be the KL divergence, but it's interesting to consider other divergences. And then we can minimize this sort of quantity. So on the next slide, I'm going to show or hint at how we can calculate something like this. We would then parameterize A and B in a certain way, maybe using neural networks traditionally now, and resort to gradient descent type steps on this objective. Okay, so we would then perform update steps on the drifts A and B. And indeed, and this is kind of a theorem, but I hope it's kind of clear after the introduction. If this is 0, then these two have to be equal. And so this should be pi 0 and pi 1. So then pi 0 is transported to pi 1 by this equation, by the forward SDE, and the other way around, so pi1 is transported to pi0 by the reverse time SDE. Okay. Again, minimizers of this will not be unique, and so this might be cause of concern. And the second line, in case you don't know variational autoencoders, then you can ignore this. But it's interesting to see that if we choose the KL divergence and we go back from the diffusion setting to discrete setting with actually only one step, then we recover the evidence lower bound that is used to train variational autoencoders. And in fact, this can be seen as a hierarchical extension or as a hierarchical variational autoencoder. Okay. So then, to make this a little bit more precise, what happens, or like give you a flavor of how this goes, we need, for example, we can choose the KL divergence here for the D, and then we write this. And so we then need to compute Radon-Nikodym derivatives, so ratios of probability measures of this form. And we can do this using the Gasanov theorem. So the Gasanov theorem in its most classical form says that if you've got two SDEs that are different or that differ in an additional drift, then you can write down a formula for their Radon-Nikodym derivatives. So for this expression, here there's a slight generalization necessary because we've got the forward and the backward SDE. And so in order to deal with this, we've got the forward and the backward path measure. There is a reference process involved, so that we kind of need to know quite well. So I'm going to skip the details here. Maybe the only thing that is interesting here, there's sort of canonical choices. You can choose for gamma 0 and gamma t. So these are the initial and terminal conditions for the reference process, and then these are the drifts. We can choose, for example, the Lebesgue measure, and gamma can be 0. But it's interesting to note that this formula, you see the right-hand side here, depends on gamma, while the left-hand side does not. And so we can really make lots of choices here for gamma, even canceling some of the terms, and possibly cancel intractable terms according to the setting. Okay. Yeah, this is just to give a flavor. It's kind of tough to understand this, but from looking at this, but you see there is contributions from the boundary conditions, and then there is a forward and a backwards path integral. Okay. I'm going to show a few examples of this. So this does recover a few important cases that, of course, have inspired this very much. So, for example, and this sort of passes a little bit to step 2 because we need to kind of take care of the non-uniqueness a little bit. One way to take care of non-uniqueness is just to fix, for example, the forward drift. So here, the idea is, let's say we're interested in this complicated blue distribution here. In generative modeling, this could be the distribution of images on the internet. Yeah? And then we choose an ergodic drift AT. Ergodic means this will be transformed into normal distribution if T is large enough. And so this AT is not going to be changed. And so this means this forward path measure, the blue one, is not going to change. It just depends on the initial distribution. But notice that the terminal distribution is not going to depend on anything, because for any initial distribution by the ergodicity, we are going to end up in this distribution. And then we can just try to learn the backward dynamics. So this was now here in red. And we can then do this generative modeling by first sampling from a Gaussian, and then applying this, like running this backward dynamics. And the so the surprising thing is that it really works. So you can So this is a famous picture by now. You can indeed then start with the high dimensional like this, which is complete noise. And then running this backward SDE, we end up with pictures like this. And so, yeah, here, this calculation uses the Gassano theorem from the previous slide. So there's some calculations involved, but this is a classical objective that you might have seen if you've seen these models before. So this is a score matching objective trying to estimate the score, so nabla log rho, from samples from a distribution rho. That's one example that inspired this a lot. Another kind of thing that's interesting is we can also, so this was one idea, we fixed the forward process. We can also fix the backward process and try to learn the forward process. I'm just showing this because it gives rise, it's interesting to compare this to what comes on the next slide. So let's say we fix the backward drift. So we're interested in the distribution. This is going to be the target distribution. And let's say we fix the backward drift of this form. Note it has a singularity at t equal to 0. So this means that, so we start here, we go backward like this. And then because the drift is so strong, close to 0, it's going to be pushed towards the delta measure here. And then it's kind of similar, a similar idea from the in comparison to the ergodic case. If we then learn the forward diffusion, that's expressions of this form, but instead of fixing this bit, we fix this bit and consider a loss function like this, then we get optimal control type of objective. So there's going to be a running cost associated to the drift vector field A and a terminal cost that depends on the density of the target at finite time t. And indeed, this kind of construction has been used for sampling as well. So we can try to sample from pi1 by solving an optimal control problem like this. And there have been quite a few works that extend this in various ways, like so. Okay. Yeah, I'm now going to come to what I want to mainly present. Okay, so we've got this step 1, which introduces forward and backward diffusions and aims to match their forward and backward path measures. Now we think about how to enforce the marginals at intermediate times. Note that here we've got strictly smaller, 0 strictly smaller than t, and strictly smaller than 1. So we fixed now the initial and terminal distribution by step 1. And now we're interested in fixing everything in between. And the tool to do this is Nelson's relation. So you might ask yourself, you've got these two SDEs, one forward, one backward. And can we say mathematically when do the corresponding path measures coincide like this? And in fact, this can be characterized locally. So this is a local condition here. This is an equation that relates the forward and backward vector fields. There is a correction term. It's interesting that you can capture this global equality constraint here by a local condition, and this is essentially due to the Markovian nature of the dynamics. Okay, so what's this correction term? Is the score nabla log rho associated to the time marginals of the path measures. Okay, so this result in some sense is one of the key results, and that has sort of started interest in this area. The idea was if we've got samples from a distribution and we can somehow estimate this score term, then we can reverse a forward diffusion by using this result. So this was the way these generative models were derived in the first place. The idea was we have a noising process like this. We want to have a denoising process. In order to make this denoising process happen, we need the score function. And so in order to do it, we need to estimate the score from available data. And this is a different way of arriving at this objective here. You can derive it from this. I'm telling you this because the idea here is in some sense the other way around. Remember that we fixed the interpolation between pi0 and pi1. So we've got all the interpolating distributions, and we assume that the scores can be tractably evaluated of the intermediate distributions. This is typically the case in the example that I showed before, because we can typically evaluate the score of the prior and the gradient of the log likelihood. Okay, so the idea is in some sense reversed to score generative modeling, because we're not trying to model the score after data, but we're trying to find a diffusion, so in some sense find data that matches the score. So it's in some sense the opposite idea. And okay, so this is the thing that I'd like to propose. I'm going to talk you through it, right? So this is just to remind you what we are trying to do. We're trying to make an SDE of this form that is controlled by phi, and so that the law associated to this SDE at every time t between 0 and 1 agrees with the prescribed laws that are constructed from the prior and the likelihood. Okay. So if you think back, the non-uniqueness in expressions of this form was there when we had completely arbitrary drifts A and B. Right? If we replace here the forward drift and the backward drift, if we write here A and B, then this expression will have infinitely many local minima in A and B. But if we enforce this additional constraint, so essentially plugging this into here is a parameterization that enforces this constraint. Then by this theorem, we ensure that the distributions agree at the time points. Since it's important, maybe I'm going to make another explanation of this. You see, if this is 0, since this is a divergence, these two have to agree. And then we can use this theorem, right? So these are the same. So that means this local condition has to be fulfilled. And then, so this means we can compute bt minus 80 and bring this to the other side. Bt minus 80 is then going to be minus the score. And if you compute this, this minus this, and you see this nabla phi is going to cancel out. And we are going to have, I have to do the other way around. This minus this, the phi's are still going to cancel out. And we're going to end up with 2 nabla v. And this has to be the same as sigma squared nabla log rho and sigma square root of 2. So by this calculation, we enforce via the score constraint, we enforce the marginals, the time marginals. So much time. Okay. Yeah. Okay. So this is the main idea. And I haven't put it on the slide, but this will in fact resolve the non-uniqueness. So you can show, it's kind of straightforward to show that this, if it has a minimum, then the minimum will be unique up to additive constants in phi, because additive constants will not change the gradient vector field. Okay. Okay. So again, going back to the slides about the Gauss-Hamilton theorem, we can compute this expression. In fact, we can play around with this gamma reference process and come up with quite a confusing array of different expressions for this, but this is kind of an interesting expression, I feel, because it looks like a little bit like an optimal control type of objective. we've got a terminal cost, and we've got some sort of running costs here. What is interesting is that it involves this backward integral. I can discuss a little bit more about the stochastic analysis behind this. But I haven't seen this type of optimal control problem before. And it's also good to write it down because it shows that everything in this expression is distractible, right? So we assume that the nabla log pi t, that these can be evaluated, and here we've only got pi 1 up to the normalizing constant, so denoted by the hat. Okay. Yeah. This is a byproduct of this construction, or it is a different way of deriving it. So we can also, by doing this, we can compute normalizing constants of the targets, of the unnormalized target pi hat. And in fact, it's a different way of deriving this. I didn't put more details here because I didn't think I would have much time to explain it in much detail. But you see, if this is an expression that we can write down for any possible control phi, and this will always, in expectation, give the normalizing constant z, because we were taking the expectation with respect to this measure, in fact, and then we just integrate about this, and we're going to get the normalizing constant of this measure. But this might have a high variance. We use a Monte Carlo estimator for this. And if we go from phi to phi star here, so towards the optimality, towards the optimal solution in the sense of this construction, then this is a zero variance estimator in the sense that we can get the correct normalizing constant without taking the expectation. So one sample is enough, and in fact, we can use any path length. Okay. This talk, I guess, wouldn't be really complete without the marketing section and the experimental results. So in fact, this does seem to perform very well. So there's competing methods that are similar. So for example, the one that I showed, which pushed the distribution backwards in time towards a delta measure, is included. And there are similar methods that involve diffusion models. But this controlled Monte Carlo diffusion model that we've been developing, this seems to outperform most of them quite convincingly, and in particular at a small number of discretization steps. So if we implement it, we need to discretize the time interval from 0 to 1. We can choose the number of time steps k. So this is on this axis. And even for quite a small number of time steps, so for example, 10, it performs very well, even in quite high dimensions, such as 1,600. There's also an underdone version of this, but in fact, the theory is still a little bit under development. But we've implemented it, and it seems to work fine. But there are some things that we don't really understand, to be completely honest. Yeah, so this is almost. Do I still have time? No.
Let's say 3 minutes.
Okay. Yeah, I can very briefly show you another kind of interesting idea, which is a little bit unrelated, but it's related in the sense that we can try to resolve the non-uniqueness inherent in step 1 in this framework by different means. So and for other applications, we might, for example, want the diffusion to be drive an initial measure mu to a terminal measure u, but in such a way that some prescribed physics is preserved by it. So, for example, some prescribed physics could be the vector field F. In a molecular dynamics simulation, this would be, for example, potential in molecular dynamics. Oh, and we want to drive the distribution from here to here, but also the modified vector field, the modified dynamics should be as close as possible to the prescribed physically informed dynamics. And this is called the Schrödinger problem often. And we can solve things like this because this kind of relationship enforces an additional constraint. Or this gives us an additional constraint. We can write down an optimality condition for this problem. So all optimizers of this problem necessarily have to satisfy this type of PDE. So it's an optimal control type of PDE, Hamilton-Jacobi-Bellman PDE. And we can use this knowledge to augment the loss function. So this was the loss function from step 1, including a forward drift and a backward drift that are now parameterized by phi and theta. So phi and theta are different. But we include an additional term in the loss that enforces the HJB equation. Okay, and in fact, this picture has been computed in this way by minimizing this expression. Again, note that this, in some sense, goes beyond the diffusion models that I showed before, where one direction of the dynamics was fixed. Here, we optimize both the forward and the backward diffusion at the same time and try to match them. Okay, so that's the main reference. Thank you so much for your attention. And I'd also like to draw your attention to this paper since it's been written by the speaker in the afternoon. And I think it's a very nice paper. So, yeah, thank you so much.
Before you ask your questions, I will repeat your questions for the teams, so don't be, yeah.
I have two very brief sub-questions. So the first one, you mentioned that there is a correspondence between diffusion models and variational autoencoders. Is it correct to say that the forward SD corresponds to an encoder and the backwards to the decoder conceptually?
I'm always getting so conceptually, I would say that there is a lot of symmetry. So you can just by renaming, at least the way I presented it, but by renaming, nothing really changes. But conceptually, so I use maybe I show on the slides. Yeah, I don't know, at least here, so that would be the variational approximation, and that would be the physical model. But yeah, as I said, I think there's so much symmetry in the whole concept that, I mean, traditionally this was thought of it like this, encoder and decoder, but at least viewed sort of through this lens, maybe this loses significance.
I think I didn't understand well the connection between the uniqueness of interpolating distributions and interpretability. If you could elaborate a bit there.
It was, I guess, it was a little bit vague. I was kind of pointing towards this Schrödinger idea in the end. So if you don't constrain this at all, then people have done this, and it kind of does work. It's numerically less efficient. It's a little bit unstable, and in particular in settings like this, you get solutions that don't really respect the physics. So there is, in fact, if you want to solve these Schrödinger bridges, there is an algorithm called iterative proportional fitting, IPF, which means that you first learn the forward process, then based on this, you update the backward one, then again, you update the forward one, then you update the backward one. And this, in principle, is guaranteed to lead to the solution to this problem. But okay, it takes a long time because you have to iterate a lot. It's also a little bit unstable because errors can accumulate, and then some papers have tried updating both at the same time. And so there is some theoretical background to updating both at the same time without adding any additional constraints. But without really enforcing, for example, this HAB type of equation, you kind of lose this interpretation. Yeah. Thank you so much.
Yeah. Thanks, Nick, for the talk. I want to ask about the interpolation at the beginning. If I understood correctly, the whole optimization is for a fixed choice of interpolation.
Yes.
Right. How do you pick that interpolation, and what a good choice? And would it be possible to run a sort of second optimization over possible choices of interpolation?
Yeah, I think it's much better.
Let me repeat the question for the online. The question is about the interpolation that you explained at the beginning, whether it's a good idea to optimize it or how to choose it properly.
Okay. Yeah, thank you so much for the question. I think it's a great idea to try and optimize this as well. In some sense, the standard choice is indeed like this. So you've got a prior H is coming from the likelihood. So it's the negative log likelihood. Then you write it down like this. But shout out to Saif, who gave a very nice talk yesterday, maybe he's in the online crowd. So he argues that this is in fact not a very good choice and you can make better choices. And we haven't really explored this, but I think it's a very interesting direction to also try to improve the interpolation. And I think that's fairly open how to do it and what to do.
Quite interested to know about the discretization you're using to chop up the interval 0 and 1, and how sensitive that might be for the number of steps.
It seems to be, so we use just the standard Euler-Majorana discretization. Yeah, in fact, it might be interesting to try different things, right? Like in the diffusion model literature, there have been some, in fact, I think by now many attempts to improve the discretization to make it more robust. In these numerical experiments, like one strength of this method seems to be that it works quite well with a small number of discretization steps. Yeah, but so it can work with 10 discretization steps, which is small in high dimensions. But
Right, yeah. And that's just uniformly on.
yeah, we typically choose it uniformly, but also I think there is room for improvement. I think one interesting thing to note is that these hyperparameters can be included in this framework. So when we write down a loss function of this form, so we optimize in phi. We might also include all kinds of hyperparameters here, sort of implicitly, and then also optimize with respect to the hyperparameters. Because sort of by construction, this might allow us to push the divergence closer to 0. And so in some sense, this might allow us to find good hyperparameters and at the same time sort of do the sampling, the optimization, and the hyperparameter tuning end to end and at the same time. Thanks.
I have a relevant question. So for the underdamped one, did you use Euler-Majorana as well, or you use this exponential integrator?
No, we used splitting methods. Yeah, so there's this underdamped version, which means that there's an equation for the position and an equation for the momentum. Or you can think of it as a Hamiltonian part and a noisy part. And typically the good way of numerically approximating these type of systems is to split the Hamiltonian part and the noisy part, and also for the Hamiltonian part you can do a leapfrog step, and that preserves the symplectic structure and so on.
Okay, so we may have the other questions in the break. So let's speak again. Thank the speaker. Yeah, Alexander. Yeah. And very cleverly, we are making a conspiracy. Right. It's the second talk. It's my great pleasure to introduce Alessandro. Actually, so it might be, I'll do it in the break. It might be a good idea to have a clicker at the end. Yes. Okay, so Alessandro has done his PhD at Imperial as well, and he has been at Cambridge and Turing, mainly at Turing, I would say. He's doing great work about a lot of different things. I'm quite curious what he has today for us. So, floor is yours.
So thanks for inviting me to this workshop. Very nice, going to be very nice to meet everybody during the break and talk about this gradient flow. So I'm going to talk about gradient flow related to a target distribution. So basically, here the motivation is you start from a common object that you have in many, many different applications, which is a target distribution that typically you write in the form, like in the talk before, as a dense with respect to Lebesgue measure. And then you assume that the density is strictly positive and differentiable, and then you define its score or its log density derivative. So I know some statisticians like to call that the score, but it's just like faster. But like you define the grad log of P, and then you kind of build some gradient method associated to this grad log P, this score. For example, in when you want to use statistical inference, you can build things like score matching or Stein discrepancy associated to a Stein operator, which is this grad log P. Fairness Stein discrepancy is an example of that. In diffusion-based sampling, you have Langevin method, Diameter method, which kind of use also the grad log of the target. Flow matching also has this form, but then the grad log P actually comes from the remainder measure of the target because we assume this is only continuous. Of course, in statistical physics, this is called a kind of canonical distribution. It's like with geometry. And but yeah, the common aspect about all these methods is that you're gonna have a target distribution which has this form. Is everybody happy with this? Okay, because I am not happy at all with this kind of object. So, and in fact, the motivation of this talk will be about understanding what actually this object is. So first, there is like some kind of canonical gaslighting about our target measure, because we have, an object that we're interested in, which is like rho, which is a measure. And then for some very weird reason, we decide to express it in terms of Lebesgue measure. But why? We already have measures, so why introduce another measure to express your own measure? Why don't you start directly with your measure and study it? So first, there is a weird reason that, okay, if we suddenly introduce DQ, why not a Gaussian measure? Unclear. Then we have some kind of like measure theoretic nonsense, because we're saying, well, I don't just express my target in terms of the Lebesgue measure. I actually want this density to be strictly positive at every point. Now, if I measure theories, you're like, wait, there's no information associated to the pointwise value of my density. Like the random Nicotin derivative is only defined almost everywhere. So what is the meaning, measure theoretically, of having a measure and using a density defined everywhere, requiring everywhere to be positive? Also kind of very unclear. Then you have some, I come more from the geometry, so then you have like a geometric abomination, which is, okay, so we have a measure, we have an object which is a measure. And then for some reason, we'll kind of define this gradient because we want to, I guess, understand it's like differential information associated to the measure. Okay, but first of all, the density, again, it's defined almost everywhere. But then, okay, sure, you assume there is a function equivalence class of, the random Nicotin derivative class, which is smooth. Okay, you take that. Then for some very arbitrary reason, you take the log. Okay, and then you differentiate that. What does that have to do as a differential geometric object with the initial target that you actually had at the beginning? And also, if now you change the reference measure, so you put a Gaussian reference measure, then you have a different density, so you have a different differential geometric information. So you have something, you try to build some kind of geometric tools which are not directly associated to the object that you're trying to study. This is also like super weird. And then you have what can be, I consider like computational objectification. So usually the reason why you say you have a log is because, like in the talk before, you know that in most applications, the target density that you have is only defined up to normalization. So if you have the logarithm, then the normalization splits, and then when you take the gradient, the normalization disappears. That seems okay. So this is kind of usually the reason why people think it's worth taking the logarithm rather than differentiating directly the target density. But okay, so this is of course important to have something that you can compute in practice. But also, I think it's also important to first understand what is the target measure, what is the actual differential information associated to it, and then how do you compute that in practice. You can also separate this question, try to first understand directly your object, and then try to, because maybe the differential information that you have with your target doesn't have this form. Maybe it's computationally intractable, but then you can think about approximating it, and maybe you can have a better understanding of your target measure. So basically, the aim of this talk is to actually understand what is the measure, and what is the differential information associated to a measure canonically. Yeah, okay. So basically, yeah, the aim of the talk is going to be mostly actually on the first bullet point, but this is part of a very long project that I'm doing with a few people, including like Michael Betancourt, Marcio Lamy, which is about understanding the differential geometry associated to measures, understand how to relate, okay, you have a target measure, but using application, you have another structure. Riemannian, contact, conformal, Hamiltonian, Poisson, you have something else that comes from the application, the way you're going to actually implement a method that's your target. So you want to kind of separate, you want to understand exactly what comes from a measure, exactly what comes from the additional structure, and how these things combine. In particular, one of the goals is to kind of perform some kind of like therapy between geometry and statistics, because the thing is that I think if you're a statistician, it's very hard to understand geometric tools like, you know, what are these things from mathematical physics, all this contact thing, symplectic stuff. Because the thing is that even if you know it's relevant, so you know, for example, Hamilton Monte Carlo or Langevin stuff, you have all this symplectic structure. So you kind of know, you know, they have some nice properties for your statistical application. But also then you want to learn more about them. So you go to a more like mathematical physics book or geometry book, because usually these are the things that study these kind of tools. And then there's so much things which are no relation whatsoever to your application, which are mixed with things which sound interesting, but also it's very hard to, they're very intertwined. So it's very hard to separate the kind of geometry and physics that is directly relevant to your statistical application to the geometry that was basically built for physics. So yeah, I think that is one of the key problems with geometry, is that it was literally built for like answer physical questions. So it's really aimed towards that goal. And it's not exactly the same goal we have in statistics, even though there's always going to be a strong connection between physics and statistics. But I think it's important to kind of, again, separate the two. It's going to become much clearer even how to like collaborate with physicists. So actually, this is actually one of the goals. I mean, I'm a physicist from training, but really my goal is to remove all the physics from statistics. So we have a clear understanding of what comes from statistics, what comes from physics, and then it's much easier to exchange method. And it's also much more intuitive for statisticians to understand what is the mathematics that is directly connected to that. And eventually, basically, the goal is to have a much clearer bridge between statistical methods and mathematics. And here, like, I like to remind the word of J. Hardy, which is the guy here. Just beauty is the first test. There is no permanent place in the world for ugly statistics, including this Gradlock score that we saw, Langevin score that we saw before. So basically, this is kind of a summary of the kind of like mathematics which is directly associated to your target distribution. And in this talk, I'm only going to mention these two ones. Actually, this one and these two here. But I think here the interesting thing is to look at the right-hand side. So basically, the left are just canonical operators associated to your target distribution. The column in the center are going to be like how they appear sometimes statistics, or even what are the mathematical properties of them. But the right-hand side is really like what is the mathematics as directly associated to the canonical structure of your target distribution. And I'm not going to go over that. But what is very interesting is to see that you have like very, very abstract area of mathematics that appear canonically. For example, things like the algebraics, twisted around cohomologies, Gerten-Haber algebra, Schirmer-Hellmuth cohomology, anti-algebraics, you know, Gaussian dualities, like things which are like really hardcore math, but actually directly associated to your target distribution. So, for example, who has ever heard about Lie algebraics? Okay, because they're going to come a lot, but and I think this is really beautiful. Like for me, actually, this is incredible, because when you come from physics, or even when you come from mathematical physics like me, what they teach you as mathematical physics, you take a book. If you want to get a PhD in mathematical physics, the books that you take, the books that you learn, you look at what are the topics, and you have everything. You have everything from functional analysis, differential geometry, topology, you know, like every math that you can think of usually is like basic training for mathematical physics. But when you're a statistician and you do like a stats degree, and then you do mathematical statistics, what they tell you is not about statistics, it's basically SDE, or stochastic analysis. If you do like a standard course in a university of mathematical stats, no one's going to talk to you about geometry, no one's going to talk to you about topology. But actually, these things come directly. They're like the foundation of your target measure. And this is because the object that you defined is not a measure. It's actually something that geometry call either a tensor one density or a two-step differential form. Basically, these are the objects which are not just measures, they also induce measures, but they also have well-defined action at every point. So now we're no longer in a setting in which you have a measure that integrates function, and therefore the value, it's kind of like that, its value almost everywhere don't matter. Like if you multiply it by a function which is one almost everywhere, you get the same measure. Now you have an object which is not rho dq, pq equal dq. It's actually rho of q equal to p of q dq. So the rho that you define, so your target measure, really has the form, it's a function on points. And what it does is that at each point, q, it assigned, like you can think about it as an infinitesimal integration operator. So what it does is that it takes like a little, for example, a sphere, a little infinitesimal volume would be like a little infinitesimal parallelepiped, like an infinitesimal like parallelogram. And what one density does is that at each point it defines like a norm on the space of this like infinitesimal parallelepiped, so something that assigns a real value to them. And so, for example, if you write your measure in terms of the Langevin kind of coordinate measure, then if you think about your infinitesimal parallelepiped, like as two vectors, they define like a matrix. When you have a matrix, you can take a determinant. Then you can take its absolute value, so it doesn't depend on the way you ordered your vector in the matrix, because it only alters the sign of the determinant. And this is kind of like how it looks like locally. It's something that takes of the function, so the fact that P at Q really matters. And then it like kind of like integrate the little infinitesimal parallelepiped by taking the determinant of the matrix associated to it. This is a very local calculation. You can think about this thing completely intrinsically. You can think about this thing without ever mentioning the Langevin measure, because in fact, there is no measure on manifold. There's no such thing as a canonical measure on manifold. So really, you think about this object as completely independent of any other measure. You just say, so in geometry, you would not say I have a measure which has a smooth density. You would just say I have a smooth one density. And that summarizes everything we said before. We make no reference to any like random abstract measure. And we'll have a lot of differential geometry associated to it. So basically, I said there are two ways to think about this kind of object. One is one density, one is twisted end form. The difference is this. So in the one density thing, you take the absolute value. And in twisted end form, you do something really amazing, which comes from Georges Derham, like one of the gods of geometry. And what Georges Derham realized is that, but the absolute value of a real number is the same as a real number times its sign. So this is kind of like something that can look trivial, because it is trivial. But it's also something that actually makes a lot of difference. Because on this kind of object, you're going to do like basic calculus. But on this kind of object, you're going to do kind of integral calculus. And you cannot, because basically these two kind of objects in many different types of geometric objects. But yeah, so this is kind of like a tree of things. You can do it in two ways. These here are canonically isomorphic, so it doesn't that makes much difference a priori, but these things embed in different types of geometric objects. And yeah, this is kind of the relation between those. So basically, as a summary, so measures can only integrate functions. The one density or twisted end form, they can integrate functions, but they can also integrate fields, like volume fields. So fields of infinitesimal parallelepipeds. And in particular, if you're a geometer, P of Q is not your density, rho of Q is. So you never ever mention P. You say rho of I have start with a one density, or even dq. Dq is actually a density for geometry. Again, not P. Okay, so now, okay, oh yeah, good. And that's sorry for that. So now I'm gonna introduce kind of the geometry of this object, which is like very deep. But if you think about measures, one of the basic structure of measures is the fact that they define a random Nicotin isomorphism. So basically, if you have a measure like rho of dq, again, so you're back to measure theory, then the random Nicotin theorem on a localizable measure space identifies equivalence class of absolutely continuous functions with, equivalence class of like functions defined almost everywhere with, absolutely continuous measures. So there's the subtleties in the random Nicotin theorem, but let's say, because you'd have to define exactly what a signed measure is. But let's say this is true because it is true if you define this properly. But yeah, you have an isomorphism between classes of functions. So functions, it's not a function, it's a function up to almost every equivalent. So there are things whose value at any point does not matter. And then absolutely continuous measure. Now, the key thing about twisted forms and the one densities is that they also have random negative isomorphism, which are much, much stronger because they are stronger objects. So when you think about rho as a twisted density, then it identifies called twisted differential K-forms with L minus K vector field. And when you think about rho as a tensor density, a one density, it identifies B density with B plus A densities. Now, I'm not going to mention exactly what these things mean because actually we don't need to know, because we'll be able to, this will allow us kind of like to remove all the abstract differential geometry and work directly with the measure informed differential geometry, which is much simpler to interpret. Basically, one example of this thing, exactly what it means, is that if you take a measure of the form PQ, F rho, which is a one density, so these things has like value at every point, then rho sharp, so this operator applied to mu q, just gives you density at every point. So this is kind of like random negative isomorphism, but which actually preserves the value at point of object, which is not what the standard random negative theorem does. So in particular, the inverse of that does the same thing as that, but with pointwise values. So it identifies functions with one densities rather than an equivalence function with absolute continuous measure. And for example, locally, this is exactly, so actually this is where geometry becomes much, much nicer than measure theories because it's much closer to what you do when you do first year statistics. You know, when you want to, for example, you have a conditional measure f of qy dq, you have a measure on the product space f qy dq dy. And then you have like kind of like the marginal measure k of q dq. Then if you remove this, when you think about the conditional density, you think about the division of that. And when you want to generalize that to measure theory, it's actually already like much more complicated. But if you're a geometer, you literally divide this by this to get a conditional measure. You don't need to do any random negative like complicated like result. You literally can divide these things because dq dy is a function. And this is a positive function. So you can always divide a function by a positive function. So it's kind of like, it seems abstract at first, but actually it's the kind of geometry tools that we'll build are much, much closer to the way like elementary statisticians think about like literally the most simple statistical objects. You don't need to get, you're literally dividing dq by dq and that gives you one. You're not taking any random negative isomorphism that then would like lose the value at points. So basically the key point about this is that now that we have isomorphism between very abstract stuff, it will allow us to take like very, very abstract differential geometry and then use this isomorphism to rewrite them in ways that we are actually the way we use them in practice, in particular for like inference and sampling with diffusion methods. And so now I'm going to start building the differential geometry associated to my operators. So there is a mother of a differential operator, which is the external derivative. It's kind of like the operator is the canonical differential operator associated to any manifold. It's an operator that derives all other operators based on extra structure. So for example, if you have Riemann metric, you can build the Laplacian and the gradient. If you have a connection or a vector potential, then you can build the exterior covariant derivative. If you have a symplectic structure, then you can build the Hamiltonian vector field, all from BSBD. If you have a Lagrangian structure, you can build the Lagrangian pre-symplectic form. But basically, all of these things, which are very important, all come from the external derivative with an additional structure. Riemannian, symplectic, Lagrangian, something, but it's that. So now that we have a measure, we can do the same. We can also define a differential operator canonically associated to the measure from the external derivative. So we're going to do the same things that geometers do for either like geometric structure, but we're going to use it, we're going to build it directly from our target distribution, which is a one density. So if you do that, you're going to get an operator of this form, which is basically so the random negative isomorphism, but the geometric one and its inverse, and then the external derivative in the middle. And what you're going to get is a map from K vector field to K minus one vector field. And that's already much nicer than what geometers have, because geometry is built on differential forms. Differential forms are very, very hard to explain. they're easy to explain for physicists because they come from physics, but like for statisticians, they're kind of like very abstract. But now we don't have a map on differential forms anymore. We have a map on k-vector field, and k-vector field are much more simple to understand. So there's several ways to understand them. I'm going to mention two. Okay, so first, locally, k-vector field is just a map that assigns to each point Q a totally antisymmetric tensor. So if you change the indices, then you get a different value, which just changes the sign. So for example, a vector field in the local coordinate is just like an antisymmetric matrix function. It's a map from point to antisymmetric matrices. But that, to be honest, that would be exactly the same with differential form. So locally, I mean, k-vector field and differential form look like the same thing. But they're not. So k-vector field, geometrically, they represent oriented k-parallelepiped. So literally little infinitesimal like volume elements. So one vector at a point is literally a direction. So in that sense, it's oriented because if you take the minus, then you get the opposite direction. A two vector at that point is like a little, you can think about it as a little parallelogram associated to the two vectors, the two arrows. And similar to vectors, just like a three parallelepipeds. So basically, k-vector field geometrically are just like ways to formalize this kind of like the fact that you don't have a coordinate system to kind of like define parallel, you know, like to define your vectors in coordinates. So you have just a tuple in Rn and then take like a matrix, but they're just a way to kind of like formalize this thing without any basis choice of like coordinate system. And dynamically, they're very cool because they're mapped, so a k-vector field, so something you can think about it locally like that, is a map from k-1 functions to constraint preserving dynamics. So this is a map that takes, for example, in the two-vector field case, it's a map that takes one function and defines something locally like that, which is a kind of like gradient flow, but it doesn't have any linear structure, that preserves the function. And this is a general thing about k-vector field dynamically. You can prove that any dynamical system that preserves k-1 function is obtained this way. So is obtained. So if you have a dynamics on any space, any manifold that preserve like k-1 smooth constraints, so f-1 k-1 function, then you can prove it's always obtained this way. So it's always obtained by a k-vector field that then acts on this function, this like in a generalized form of this, and then gives you this dynamics that preserves the functions, the level set of the functions. So basically, geometrically, k-vector fields are just like little volume elements, and dynamically, they are the generators of constraints preserving flows. So any flow that preserves constraints is generated by a k-vector field. So how does the curve look locally? So in local coordinates, some of you will recognize this expression. So you take a V like before, a k-vector field, then local coordinates. This looks a lot like 1 over phi. Then you take the derivative, you contract over the j. So here there's a sum over j. And then you just have k-1 coordinates left. So it's a map from, again, you lose one coordinates. You have a k-vector field, which have like k indices, and now you have k-1 indices. Now, if you, for example, are familiar with Stern operators, then you know that in the case k is equal to 1, so for a vector field, this is exactly what people call the canonical Stern operator. So it's a map from vector field to functions that then you use to build like the things that integrate to 0. If you come from Riemann geometry, then usually your P will be like the square root determinant of the metric, and this will cover the Riemann divergence. And there's like a lot more. This is as a much. It's an operator which has a long history, which appears in many fields. Much prior to canonical Stern operators. For example, in supergeometry, this is called the odd Laplacian, because actually you think about it as a second order differential operator, like a Laplacian, on a super manifold. So basically your vector fields will not just be function of x, they'll also be function of like things like odd coordinates. And then you will reinterpret this as second order differential operator. So that's how it occurs in supergeometry and quantization. In Poisson geometry, it comes from Kosul. So usually you don't think about it as associated to a measure, you think about it as associated to a connection. But it's not the connection divergence. That's a different thing. Okay, so the key thing is that this is an operator which is directly associated to rho, not log density. And one thing though is that this is why geometry is important, because if I just write this locally, I mean, then why is it only applied to V, which are totally antisymmetric? I mean, if I write this thing here, I could put any matrix function, for example, and I could still calculate this thing. That seems like something I can do. At least I can write it. But that thing doesn't represent anything, or at least it doesn't represent anything associated to rho. So the difference between the curl, like this curl of associated target distribution, for example, the divergence associated to a connection, like a connection, is that it only applies to very specific cases, only antisymmetric stuff. If you have a Riemann divergence, this would apply to all tensor fields. The Riemann divergences are much stronger objects. Okay. In particular, unlike Riemann divergence, the curl is a homology boundary operator. So that means many things, but in particular, it means that its square is 0. It's a square node operator. And what it does is that it characterizes all measure preserving systems. So whenever in any setting you have something that is measure preserving, it comes from the curl. So for example, the rho preserving diffusion always have like this form on any manifold. So you're parameterized by choices of two vector fields, or like antisymmetric matrices in Rn, or vector field, choice of vector field, which just represents your noise. And gamma here is a term. So here to prove that any rho preserving diffusion has this form, you need to take into account the topology of a manifold. This is not easy to do, but geometers do it for us. And like basically this gamma is something that becomes to think of like the twisted cohomology, the twisted Garand cohomology. It's just, yeah, something that basically the geometers will tell you, or if you're on this phase, this is the family of this gamma. But basically, as up to like topological obstruction, your measure preserving diffusion is just the curl of like two vector fields and vector fields. So any measure preserving diffusion has a very, very simple form. This is actually very useful for geometric integration because this is what geometric integrators call like generating forms of basically like a geometric structure. So basically when you're in geometric integration, so for example, before we talked about Hamilton system, you have a symbolic structure. So you want to write, if you think your Schrödinger structure is important, then when you discretize, you want to start with a Differential system and then discretizes in a way that you preserve whatever structure you had at the beginning. And so, for example, if you have a system, you want to write this in a generating form so that you can split, for example, the Hamiltonian, then you're going to get different vector fields. But if you integrate those exactly, then you obtain like a numerical integrator, like leapfrog, that exactly preserves your geometric structure. So here's the same. We don't have a spherical structure. We have a measure, but we have some generating form in the sense that if we split A, and if we split the vector fields, then this like things becomes a sum. And so we can split the diffusion into like measure preserving parts and do like a splitting method, which exactly preserves these geometric parts to be measure preserving, and then you compose it. So this gives you a way to build a splitting method for like measure preserving diffusion without any other structure. Okay, so I'm going to mention how much time we have. You know how much time?
25 minutes.
Okay. Okay, good. So I was about to skip this slide. Okay, so one beautiful thing about one density, so measure which are values at point, is that by the thing I just mentioned, they define canonical maps from two vector fields to measure preserving vector fields. So this is the map. It just takes a two vector field and it gives you like a measure preserving vector field. This is actually something very, very special about this one density. It doesn't apply to, for example, direct measure. Well, to direct measure, you almost can, but it doesn't apply to non-smooth measure. So things which don't have this kind of like nice values at points. So you have a map, two vector field to measure preserving stuff. In particular, in Hamiltonian mechanics, the A that you choose is the Poisson structure. So if you're a physicist, you think of Hamiltonian mechanics as you have a Poisson structure, you have Hamiltonian functions, and then you map Hamiltonian functions to Hamiltonian vector field using your Poisson structure. And this makes sense for physicists because that's how the physics emerges. It's all in the Hamiltonian. But we're statisticians, so we don't have Hamiltonian. We have measures, or measures of the format that I mentioned before. So actually for us, Hamiltonian mechanics is no longer a map from functions to Hamiltonian vector field. It's a map from measures to measure preserving vector fields. This is very nice because already it tells you, for example, for HMC, it's always very weird because you start talking, you start saying I have a sampling problem with a measure of the form I mentioned above, and we're going to solve it with like complicated symplectic geometry. and I need to write my density in the Lebesgue form. Then I need to take its log density. I don't know why. Again, the Lebesgue measure, and then I need to lift it on to a symplectic manifold, and then the symplectic measure will appear, and that's going to be my Hamiltonian vector field. So you have a super complicated, like you need to build this thing, and then you need to justify it. But once you understand a bit more the geometry, then realize actually this is not what's happening. We have a Poisson structure, it's actually a vector field, so it's exactly in the form that we needed to map measures to measure learning system. So once we decide that the Poisson structure is useful, which then is left to justify. But if we start from a Poisson structure, then we canonically get a map from measures to measure learning system. And now the fact that you're going to get a log density is a theorem. So basically, the fact that you can write the curl of this thing as a basic gradient system is it's not just something that you build ad hoc for no reason at all. It's something that comes directly from the fact that the symplectic measure, the curl of the symplectic measure of the Poisson structure is 0. And this is now a theorem, which is like a very strong dynamical interpretation, which actually is very important in HMC. Because now we can interpret what it means to have vanishing curl. So I introduce the differential operator, it's cool. But what does it mean when you have elements of its kernel? So what does it mean for curl of a k vector to be 0? This is equivalent to the fact that the Nambu dynamics, Nambu mechanics of CTV is measure preserving. So what that means that before I told you that you can interpret k vector field as a map from k-1 functions to vector fields. So think about Hamiltonian mechanics. In Hamiltonian mechanics, you have a Poisson structure, and you have a map from all Hamiltonian to all possible functions to Hamiltonian vector field. Saying that Hamiltonian mechanics is measure preserving would mean that all these vector fields are measure preserving, not just one, like the entire family is measure preserving. And much more generally, you can consider Nambu system for many constraints. Again, saying that the Nambu mechanics is measure preserving is the same as saying that for whatever choice of function you choose, the dynamical system you get will preserve the target measure. And this is equivalent to saying the curl of V is 0. So again, this is super nice because if you start with geometry, then you have the external derivative. And you can, usually people will study closed and exact forms. So for example, closed form are differential form that satisfies d alpha is equal to 0. But then it's going to be very hard for us to interpret what these things mean, because again, they come from physics. So there they have a good interpretation, but for us, it's very abstract. But actually, when you have a measure, then you no longer have an external derivative, you have an operator curl, of which the element of its kernel have a very, very easy interpretation. So again, k-vector fields are more simpler than differential form because you can just think them about family of dynamics. And then curl of those things being 0 just means that the associated mechanics is measure preserving. So super simple to interpret. You don't, you can just draw pictures. And this fact is actually a key property of Hamiltonian mechanics when you do bias correction. So whatever bias correction mechanism you use, whether you use also metropolis or more advanced types of bias correction, the point is that these things are going to depend on your Jacobian. And the Jacobian will be based on basically, so usually you have a splitting method, but if all the element of your split preserves the reference measure, then the Jacobian will just be a density ratio. And this is true for this entire family of preserving dynamics. So whenever you split these things, then you're going to obtain some which is preserved like some kind of measure, but each element of the split preserves the measure. So the Jacobian will only depend on the ratio of density. I mentioned that, but now we measure and formed the most simple operator of differential geometry. But now that we understand how these things work, we can do something much, much hard, which is not just characterize systems that preserves a measure, but also systems that preserves a measure and arbitrary smooth constraints. And this is the same theory that all the things I presented all in the same way. The only thing is that you replace external derivative with the foliated external derivative. So it's like a derivative that automatically takes into account the fact that you have a constraint system. So means you have a manifold, and then you add the information that you have constraints, and geometers are able to encode that. It's hard, but it's called the foliated theorem homology. It's something that is studied. And then now that you have a measure, okay, so you have something very abstract. You can do the same things I did before. And then you can prove that all row constraint preserving system, whether it's diffusion or the numerical system, all have a certain like very specific form. So for example, in the case of diffusion, if the constraints are given by F1, Fk, then you're gonna like some like k plus 2 vector, k plus 2 vector field, k plus 1 vector field, or something like that. I think, k plus. There's gonna be a k plus 2, k plus 2 vector field and k plus 1 vector fields. And this gives you a generating for all systems. So again, you can just choose your Z, choose your V, and this gives you all possible system of like measurement constraints. So here I didn't include, but like before, you have a little term that represents the topology of your constraints. It's something that is associated to the foliated rank homology. But yeah, that gives you a very nice derivation and just proof, just theory of measure constraints for the system directly from a target measure. Okay, so now you're all tired with my operator curl, but it is a very cool operator that describes all like measure constraint stuff. But this is just that. So we're here. And actually, we're not even really here. But anyway, I will pass to the second operator because the curl is the one that is associated to HMC, Langevin stuff, all diffusion processes. But now we're going to talk about the operator associated to statistical discrepancy, score matching, KSD, KL, whatever, like all these kind of things. And the cool thing is that, so you see now when I mentioned, I never actually mentioned the log density. I had a measure, I built an operator, and then I built all my diffusion processes that sort of measures upon that. And then in some cases, like Hamilton mechanics, then my log density arrived for like a very specific dynamical reason. But I didn't build it a priori. Now the cool thing is that we're also going to get a log density score matching, because these things appear, but it's going to come for very, very different reason. And in fact, it's not really the same score. So basically, one key point is that this score that we define here for no reason actually come from different differential operators, which have different interpretation, and the scores come from different reasons. So now we're going to move on to what is actually the score of discrepancies. Okay, so actually, we're going to do the same thing. So we're going to take our third derivative, and we're going to measure for it. And I might be confused because this looks like the same as I did before, but it's not exactly the same because before my P sharp was here and my rho flat was there. So this is almost exactly what I did before, but in the opposite direction. So this is like another put an operator associated to the target density, but it's very, very different from the curl. And now it defines a connection. Actually, it defines a lot more than stuff, but now I'm going to restrict its application to measure. And when it applies to measure, then it defines a connection on the space of measures. So by construction, the type of measure we defined in the first slides define like curvature, they define covariant derivative and things like that on the space of measure. In particular, if now I choose another scope measure nu, and I apply the covariant derivative, then I have a very natural statistical discrepancy in the sense that the covariant derivative of 0, the covariant derivative of nu respect to rho is equal to 0 if only rho and nu are equal everywhere. Not almost everywhere, they not measure their one density. So this is like a pointwise equality. And now this is something I think is so beautiful. But if now I express nu in the form QDQ, we can express it like locally in local coordinates, and I'm going to get rho all times derivative of Q over P. Now, if my Q is positive, like strictly positive, so it's like the one I had before, then I can also write this. Oh, sorry, this should be a nu. I can also write this in a logarithm form. So kind of like the d log of something that in the first slide kind of like appear, but it's coupled to something, and also it doesn't actually really appear. It's just like the logarithm is kind of in your head. Like you can write it down if you want, but really this has this form like that. And now I'm going to come to why this is super important. But first, what does this thing mean? So if I take the covariant derivative along a vector field, so I'm back to my sphere, I take the trajectory of my vector field. So I have in Q times the direction. What these things represent is that this will be a measure. So it will be a one density, so it will be a measure with pointwise value, which if it is positive at a given point, represent the fact that as I move on X, the norm that nu gives to infinitesimal parallelepiped will increase relative to the norm that rho gives to infinitesimal parallelepiped. So it's something that defines how these like smooth measures behave as I move along trajectories of a vector field. So this is kind of the connection interpretation of that. But if we go back, to this expression that I thought was very nice, if you kind of go back to the curl, so remember the curl, like if you think about it, for example, standard operator kind of perspective, think that's the classic 1 over p derivative p of something. The connection is kind of the opposite. The connection is kind of like p d 1 over p q. So it's kind of like, it's just inverting how these things act. But in fact, so here it already tells a big difference between the curl and the connection. The curl never need a reference measure. So when you build measure predictive system, you never need to mention any reference measure. They come after, but in principle you don't need to. While on the other hand, the connection acts on measures. So in that context, it's very, very natural to actually have two measures and to get like some kind of like ST ratio out of it. Now, the key thing is that this is actually a Algebraic operator like your Nadal of P. And this thing, so if we go back to explaining logarithm form, this is going to be the correct log density differential information of the theoretic density, not this thing. So you always need to tensor this thing with whatever reference measure you chose. So this is kind of what happened here. You don't have just like a derivative of like a function. You always have a measure associated to it. So this is like a measure value differential form. It's not like a different, this is a differential form. This is a measure value differential form. And this is super important because now, still, the operator does not depend on the normalization constant of rho, which is what we want for applications. However, it does depend on the normalization constant of nu. And this is important because now the rho acts as a differential operator on nu. And differential operators are linear. So if you go back to nabla, just this thing, nabla log q over p, so you have two measures. Now this does not depend on the normalization constant of neither q and p. So it does not act as a differential operator over q. But this does. Like the full thing does act as a differential operator over q. And if you're like a geometry, you're very happy because if you have a differential operator of something, that means you can extend it to whatever is the all distributional elements of all distributional objects associated to it. So what it means is that if your differential operator, for example, acted on smooth measure, like it did now it actually can act on all measures, even the Dirac measure, even the Schwarz distributions, whatever, it doesn't even need to be a measure. Because it's now linear in nu, nu does no longer need to be smooth. And in particular, all like main types of discrepancy will emerge by just applying this like covariant derivative to non-smooth nu in that way. So really just by tensoring this weird thing with dq, we've obtained something which is now as a strong geometric background and also as a differential operator. vector field. So all these are actually very different operators. But what Derham wanted to do is to say, okay, they're different, but I do want something that tells me what is common about all these different objects. And so he built what are called Derham current, which are a way to say if basically I can derive a single operator called the homology boundary operator of Derham theory, of which all of those are going to be special instances when I apply on a certain type of object. So this kind of like homology operator acts on like super general objects, but then on specific objects is going to recover this like free derivative and other types of derivative. So basically Derham theory, from the point of view of Derham distribution theory, is about unifying all of like differential operators and then understand the relation between this differential operator and the topology of a manifold. But yeah, basically, just very quickly, what do you need to differentiate? You need a topological vector space structure. This is because basically the derivative is always defined as a limit of a substruction. So if you have a substruction, that means you have a vector space structure. And if you have a limit, that means you have a topological structure. So basically, that's why all these topologies and topological vector space of Langevin comes in, is because when you just think about what is their differential in a very abstract way, you're going to have to build topology on your space of measure and a vector space structure in your space of measure. In particular, if you try to, now you have a measure mu, you can push forwards on a flow, along that flow, you're going to get a curve on the space of measure. On the space of measure. So if you build a certain topology on that space, then you can now prove that this limit exists, and you can define that as the derivative. So in particular, you can always prove that this limit exists when you build a appropriate topology on the space of differentiable complex exponential function, and then you can induce topology on this as well. And for example, so standard result in distribution theory, if you differentiate this measure, so long as differentiable, it's basically 1 until the 0. It's basically log until 0, and then it's 0. So it's no longer smooth at that point. And if you differentiate, you're going to get the direct measure at 0, which makes a lot of sense, because away from 0, this is kind of like a flat measure, but at 0, something weird happens, and this is why you get specific direct measure at 0. Similarly, if you differentiate the direct measure, well, what does the direct measure do? It evaluates function at points. So if I change a bit the value at points, well, that's actually exactly like taking the derivative of a function. So derivative of functions tell me about the local information about how much function changes, point-wise. So it makes a lot of sense that the derivative of the direct measure would be like a differential operator evaluated at x. So this is not just abstract theory, it's actually very intuitive when you think about what these things actually mean. Basic short distribution, in one point, is a theory that unifies integration and differentiation. So you can prove that any Schwarz distribution of order L is a linear combination of different operators of order L and integration. So everything that looks like integration and different operators is a Schwarz distribution and vice versa. Which is cool because in statistics, we always have a mix of integration. Well, we often have a mix of integration and differential measure. Okay, so now we kind of have at least some intuition about how differential operators are extended to non-smooth objects. And now we know that, as I mentioned before, that nabla rho acts as a differential operator of mu, so I can extend it to all Schwarz distribution. And basically, all the standard form that I get of this log density derivative, so in the context of if nu is actually like a measure which like a one density, so something smooth which has value pointwise, then usually the differential information would be the nabla log nu over rho, and so I recover that when I apply to measure that form. If now nu is only smooth, is no longer necessarily positive, then the differential information actually is this thing kind of acts like the derivative of the ratio. So I don't have any more logarithms, so my logarithm disappeared, which is great because it's not a differential operator. If I have a measure, which is a real measure, but it's very close to a one density, the Bayesian measure, which is absolutely continuous, is kind of like an equivalence class of functions. You can think about it that way. And if in that equivalence function you do have a smooth measure, then this object will act in the way of score matching. So score matching, the way it acts on function, is it takes the grad log nu of rho, it applies that to a vector field, and then it integrates. This is kind of the way it applies in score matching. Well, if you do standard discrepancy, you will usually start from actually this operator. So you apply the divergence, so the standard operator as if you have vector field, and you integrate, and you call that the standard discrepancy, or at least the supremum of that over like a set of vector field is what you call the standard discrepancy. But basically now you have a single operator that does everything. It just depends on the regularity of nu. In particular, so the classical score is written that way. So matching is just the norm of this thing in L2. Differential matching is just the norm of this thing composed to like a linear functional vector field. Diffusion KSD is just the norm of this thing in like a matrix valued kernel. Cool, but like the divergence of the thing. SVD is just like the mean embedding of this thing, because this is a continuous linear functional. So you can mean embedding in RKHF under certain condition. And then you get SVT flow. But all of this comes from a single operator, which is direct associated to eigenmeasure. And you see the fact that you didn't have a log to start with. Because if you have a log, then this only applies to functions which are the same equivalent, like they're in the same, they're equivalent functions. But in KSD, we have very, very unequivalent function because rho is very smooth and used typically like a discrete measure. But the fact that we have this additional tensor solves completely this issue. It kind of already acts in exactly the way we want to act without any assumption, aside from the regularity of nu. So in particular, if I just have a quick application of that to KSD, you can prove that KSD, so if you have a base kernel K, matrix value kernel, you build this like Stein kernel, you build a third-hand RHS, and then what you have is that, so KSD at this form, so separating nu from rho in standard RHS is exactly the same as separating this Schwarz distribution. It's not actually a Schwarz distribution, like it's not even a direct current, it's something slightly different, but it is like a distributional section. That's how geometry would say. But really separating nu from rho is exactly the same as separating this like Schwarz distribution from zero. And this is actually the kind of like geometry we use in a paper with Lester McKay and Claudio and Simon Gabriel, when we, for example, derived a new condition to much more general condition to prove that KSD control with convergence, control Wasserstein convergence, and also when we build the first bounded kernel that exactly makes with convergence, is not all based on this like Schwarz distribution theory of this operator. It's kind of very cool because we actually ignore completely the literature, like the previous literature on like the theory of characteristic KSD, so the kind of like standard which are characteristic and control convergence, because we don't need to. Because this is kind of a distribution, which means that the one part already tells us everything we need to understand about these things. And so we went directly to the paper from like 1960s. And then we used whatever Schwarz told me about these things. And then we just applied this to KSD and we got like some like super good results. Okay, so I'm almost done. So yeah, I know I've been through a lot of stuff. But here are a couple of key points. If you have a measure of the form that we mentioned in the first slide, it's not a measure. It's a geometric object, which is either a twisted form or like a one density. The one density has two chemical differential operators associated to it. It actually has a lot more, but let's just focus on those two, the curl and the connection. The curl describes all observing system. The connection describes curvature-based discrepancies, which are not all discrepancies, but there are a lot of the important ones. In particular, the grad log P that comes in HMC and the grad log P that comes from matching comes from different reasons. So in HMC, you have this operator, and the score that you get is this thing, which is a map from multi-vector field, so from K vector field to K plus one vector field. So in HMC, you would apply this operator to a Poisson structure, which is like a two vector field, and you would get like one vector field, like a dynamics. In the context of score matching or similar types of discrepancy, you don't have like a log always. You have this kind of like score. And this is an operator from vector field to measures. So slightly different. There are some relations, but they're like quite different. And the last slide. Good. 1 minute. 1 minute, okay, perfect. So this is just, as I said, I have before this start of this talk, like unraveling a geometric conspiracy. This is like step 2 of the geometric conspiracy out of like 20. Basically, there is so much beauty in this kind of like object rho, but you cannot understand it if you just think about rho as a measure, because geometry and measure theory are so I don't want to say that they are, well, they're kind of inconsistent actually. They're based on different structure. They're like, there's no, ideally, if you're in geometry, so for example, geometry and topology are consistent. So if you're in geometry, you build something at geometric results, and then you say, okay, ignore geometry, which means that you have a functor from the category of differential geometry, the category of some kind of like topological category. Then you apply the forgetful functor, and then you get whatever result you have in differential geometry, and you obtain a topological result. So this would be like, oh, I have a smooth measure. Oh, actually, wait, it's not smooth anymore. Or actually, I don't care if it's smooth. And then you apply this forgetful functor, and that tells you, okay, so these things that no longer exist, because these were like specific to differential geometry, but these things are now the same result, but more general in topology. So mathematics is built in a way that you start from something very, very nice, and usually the nicest things are like linear algebra, or like things like that, then you have differential geometry, and then they become more and more ugly, or less and less structured. But you have like a very clean way to go from one to the other one. But you don't have a clean way to go from geometry to measure theory because of the way measure theory has been built historically. To connect measure theory and geometry, you actually need to go through von Neumann algebras. So you need, because actually measure theory breaks very, very easily as soon as you consider constraints. So you need to rebuild measure theory out of von Neumann algebras. So basically, it's kind of like very hard for our statisticians because we're usually told that the mathematics of statistics is measure theory and SDEs. And this thing is very inconsistent with the actual mathematics that we use in our methods, like gradient flow, stuff like that. The end goal, well, it's not the end goal, but actually key thing is that all the things I mentioned, they're all essentialized in Lie algebroids. So Lie groupoids are the group version of the algebroids. They're just things that describe symmetries, but not the same way we did like 150 years ago. So if you look, for example, at geometric deep learning, you look at Michael Bronson's book, he will tell you, and his co-authors, that the kind of like blueprint of geometric deep learning is to look at the group theory of the set, of the, if you have a manifold, you have a, kind of like a group structure, you have an action. If you have networks, you have a different action. But basically, the idea of geometric deep learning is to take this kind of like group theory kind of ideas from symmetries, and then build them into your architecture of deep learning, and this is how you get geometric deep learning. The point that the groups are like, they are 150 years old like objects, so they're great, but they've been surpassed. So basically, they're not enough to describe all kind of symmetries that we need to. For example, in statistics, we have conditional expectation, which are these integrations. So they're kind of like measures which are associated to like a foliation of your set. So you kind of like have a set, and then you divide it into like kind of like hypersurfaces, and then you have like distribution of each hypersurface. These are type of like symmetry of your space in terms of like this decomposition, which you cannot describe by group theory. So you need something far like stronger, which is called like Lie groupoids. The algebraic is the infinitesimal theory of that. Yes, for example, foliation is an example of thing very important statistic, which is not described by groups. In particular, what you can prove is that for any Lie algebroid, you have three canonical operators associated to like a generalized type of measure. So for example, in the context of foliation, that generalized measure is no longer a measure, it's a conditional, it's a disintegration, so it's a family of measures. For any such object, you have three operators, they're equivalent in an algebraic sense. The thing that I said, for example, the thing that we use in multiple system, the fact that the square of this is 0, is equivalent to the fact that this thing is a flat connection, which is equivalent to the thing that this thing is a derivative of a bracket. It is just to say this is like a very abstract theory, but that actually essentializes all your calculus of the measure. And in particular, last thing I mentioned, this thing. So it allows you to build, if you have the idea of generative deep learning, you have additional data from symmetries, and you build it into architecture. The algebraic do that automatically for you. So if you have like additional structures, symmetries, constraints, foliation, and a lot more structure, all of that is directly encoded in your the algebraic. So for example, this is how we went from characterizing measure controlling system to measure constraint controlling system in one step, because actually I just changed my algebraic. Okay, I'm gonna finish that.
Okay, let's
Thank you.
take the speaker. Can you repeat the questions when they ask from the...
Oh yeah, you mean loud? No.
Yeah, because of the microphones, online people. Okay, are there any questions? Yeah.
So just one question. So, the approach of the RAM and also this Lie algebroids, do they also describe unified discrete geometry, discrete exterior calculus, that also falls in?
So basically the question is whether the algebraics and the RAM stuff also apply to discrete analogs of differential geometry.
Yeah, discrete theory of calculus.
Yeah. So partly yes. So for example, the actual big theorem from the RAM was about you had extra calculus of smooth object, and you wanted to associate to like homological calculus of chains, which are no longer smooth. So there's a kind of thing that you have in like data analysis, like it's kind of like singular chain complex. So basically the idea of the RAM, you have like strong connection between smooth geometry and non-smooth geometry. Of course, some things will break when you kind of like go down to like discrete stuff, but there are also like strong relations between them. And the algebraics definitely. So the algebraics basically, so for geom stuff, yes, but it can be completely like you lose a lot of stuff when you go from smooth to discrete. For the algebraic, yes. So basic group rates, they're like the most general like ways to think about symmetry. So they describe both like smooth and unsmooth. And not all of these group rates will have a smooth structure. And the one, basically the group rate will tell you whether it's smooth or not. And if it has smooth structure, then the smooth part will be described by the Lie algebraic. So this is exactly like in Lie groups and non-Lie groups. So groups are like can be completely discrete, but if they have a smooth structure, then you can prove more stuff about them, which comes from the Lie part of the group. So there are a lot of things that actually, so for example, these things are very important in physics because they allow you to kind of unify internal and external symmetries, which are discrete, some of which are continuous. So the answer is kind of yes, but how much yes is summarized in exactly what group rate and exactly what the RAM cohomology you have. But yeah, we can talk, yeah. But
There is an online question. So are there natural distances between Lie algebraics?
yeah,
Lie algebraics.
yes, actually, yeah, this is so beautiful. Thank you. So as I mentioned, in the case of smooth measure, we had a curve which represents measure building system and a nabla rho which represents discrepancy. But this is true for all the algebraics. So for example, in the case in which I have my algebraic set to foliation, rho is like not a measure, it's like a family of measure, as I mentioned before. And now the curve represents the system that preserves all the measures in that family, while the nabla defines a discrepancy. So for example, this defines a discrepancy between like a disintegration and another disintegration. So it's like a super generalization of like things like SM and KC, which applies to not just measures, but like family of measures. In particular, what is cool is that, just a quick answer on that, but like if you come from KSD, and usually the way you go score matching is you start from KSD and then you do like something like integration by parts to recover score matching and KSD, like cannot relate to two. So in some sense, in the case of KSD, you have a relation between that and that by integration by parts, which is not the core structure, but it's something that you can prove. This breaks down for more general algebraics. For example, it breaks down for disintegration. So in that case, this is no longer the transpose of that. Like it's no longer if you do integration by part, you no longer go from this to that. It's no longer true. But yes.
So one more short question from Tobias.
So my understanding is that you introduce all this language in physics because you have a lot of symmetry or gauge invariance, things like that. But you would not really use that language to compute correlation functions or more concrete things. So in statistics, what's your vision of how you apply this kind of language? When should you learn it? Is it for more elegant proofs, or can you do something?
No, so for me, I think the goal of that is not to make statistician geometers or to make geometers statistician, but is to really clarify the link between these two things. So ideally, what you want is you have people. This is what I see physics. You have people which are experimental physicists, which understand the experiments and the relation between experiments and basic physics. Then you have like mathematical physicists, which are something that they don't understand that much experiments, but at least they understand the formalization of the experiment from experimental physics, and then they understand the structure of that. And then you have mathematicians, which are the next level. They just focus on mathematics, but you have like a clear way to communicate between these people. The problem is that we don't have that in statistics. Because of what I mentioned, because like mathematical statistics has nothing to do with mathematical, like what people tell you is mathematical statistics is not really, it's only a little part of what is mathematical statistics. So ideally, we want to be in a scenario in which you are interested in correlation. Then you come up with the thing you want to calculate. And then you go to someone which is like the more theoretical part, which tells you, which kind of try to understand exactly what structure you have, exactly what assumptions you make. And then it goes back to kind of this kind of geometry and tells you, oh, okay, this is kind of what I think the structure is, and therefore these are the kind of tools that come with it. So this is how I see things. There's like, it's exactly the same in physics. The point is not for everyone to know everything, because that's impossible. The point is that for people to be good at what they do, but then have enough common language to be able to properly communicate with, properly understand, have some intuition about. If you're a physicist, you don't know maybe you don't know general relativity, but you've been ingrained, because you've heard about the fact that general relativity is related to curvature and real metrics. But maybe you're specialized in another area of physics, but it's common knowledge that this is what general relativity is about. This is kind of the same thing I want for statistics. I want even like more applied people to not know the geometry, but at least see, oh yeah, I've heard this is related to like a weird like connection thing, and then go to someone and tell, to have a discussion and basically see how much the geometry can help you.
Yeah, it's almost coffee time now, so
Yeah.
let's thank the speaker again.
Thank you very much, Anna, for joining us today. Thank you, everyone else, for joining us for this workshop. So, Anna Korber did a PhD at Telecom and High Tech a few years ago, and then after that was a postdoc in London, UCL at the Gatsby Institute, and now she's an assistant professor at Institut Polytechnique de Paris, and she's going to be talking to us today about something with modified interaction and energy dispensing. So, Anna, take it away.
Thanks a lot for the introduction, and firstly, thanks to the organizers for organizing this great workshop and inviting me. I'm sorry I couldn't attend in person, but yeah, so here I am still online. So yeah, indeed, I will present some recent work entitled Sampling with Modified Interaction Energy Descent. That is a joint work with people from MIT and University of Texas, IBM Research, that was accepted to a machine learning conference a bit sooner this year. So the main goal of this work is to do sampling, and I will first talk about what we call unconstrained sampling. So the goal is to approximate a target probability distribution on RD with a density denoted mu star with some discrete probability measure. So think, for instance, of this target probability density mu star on the left, and on the right, some discrete approximation. So here, it's samples from mu star. And the generic task is to approximate such a probability density, for instance, to compute approximate integrals, where you want to integrate some function f with respect to mu star that would be approximately this finite sum if you have an atomic measure supported on these directs approximating mu star. Okay. Feel free, of course, to interrupt me at any point if you don't hear me well or if something is not clear. So the main motivation for this task is Bayesian inference. So I know that many people here are familiar with it, and Nicolas Nusken, for instance, earlier this morning introduced some notations as well, but I will reintroduce them at least to settle my notations. So the goal of Bayesian inference is to learn the best distribution over some parameter that is called x here of a given model to fit observed data. So think, for instance, that you have a data set D of ID examples. So couple variables wi that have features describing an image, for instance, and yi that is the label associated to that image. Okay, so you have PIID samples of the data. And second, assume an underlying model parameterized by some parameter x in RD, describing the label y. So y is assumed to be a function g of the input w, the image you feed to the model, for instance, some parameter x plus some Gaussian noise. So once you have assumed this, you can write the likelihood, that is the probability of observing the data given some parameter x. Under the IID assumption is the product of individual probabilities of the data labels given x, the parameter, and yi, the input. And second, under the Gaussian model, it writes as exponential minus something that is a loss. So the difference between the true label yi and the prediction by the function g for the input wi and the parameter x. Okay, so this is step one. And step two, since you want to learn the best distribution over the parameters x, you need to start from somewhere, from initial guess. so this is a prior distribution. You assume that the parameter x is distributed as P naught. For instance, P naught could be a standard Gaussian. Okay, so from there, Bayes' rule gives you the formula for the posterior distribution over the parameter x that is best fitting the data you have observed. So the posterior distribution of the parameter x given the data that you have observed is equal to the product of the likelihood, so probability of data given x times the initial guess, the prior, divided by z, that is the normalization constant. But this guy, in general, especially if you use a complicated model function g, is intractable. Okay, so in my talk, mu star, the probability density I want to approximate, is typically, in the setting of Bayesian inference, a posterior distribution on a parameter x of some model. And mu star writes as so the density of mu star is known up to a normalization constant, thanks to this formula, and you can write it with the examples I've given as exponential minus some function v, where v, the potential, is the sum of a loss term on the data, plus some regularization coming from the prior choice. Okay, so this is my goal. Why do we want to do that in Bayesian inference and machine learning in general? For two goals. First, if you have a distribution over the parameters of your model, you can predict with uncertainty. That is, if you give me some input w, the output of the model, the prediction is g of w x if you have a fixed parameter x, but if you have a distribution of x, you have a distribution on the output of the model. Moreover, you can aggregate all these outputs, which is typically done as Bayesian model averaging. If you only want a pointwise prediction, you can output y hat, that is the integral of all the predictions of the model parameterized by x, where x is reweighted by the posterior distribution. So you can see this as ensembling a lot of predictions of different models parameterized by different parameters. So in this talk, when I refer to the task of sampling, I want to build any approximation mu m, discrete one of mu star, not necessarily on empirical samples. Okay, and you can think of this image where you have an input w, for instance, the image of a cat described by some pixels. You have fixed a model G. So here I have fixed the architecture of some neural network. You have different parameters parameterizing each neural net, x1, x2 to xm, and you can use all these pointwise predictions for the Bayesian model average. So typically to solve this task, you can refer to many methods were developed in the literature, and I will first talk about the non-parametric ones. So historically, maybe the most canonical methods belong to Markov chain Monte Carlo techniques, where in this case, the goal is to generate a Markov chain in RD, whose law converges eventually to mu star. Okay, that is exponential minus v. And the most canonical algorithm maybe is Langevin Monte Carlo, that would update the position of a particle this way. So think of, here it's a banana distribution in 2D, and the particle at time m is pushed from its previous position, minus a step size times the gradient of the potential at xm, plus some Gaussian noise rescaled with respect to the step size. And here, for this method, you use, for the discrete approximation that would approximate mu star, you would use all the iterates, all the previous iterates of the algorithm. And more recently, at least in the machine learning literature, alternative methods based on interacting particle systems were proposed. And here the goal is a bit different because you will use a set of n initial particles whose positions are updated. Each particle is updated at each time, and you use the final configuration of the particles as the approximation of mu star. And this algorithm introduced by, so in particular Kyung-Liu, that we'll speak a bit later today, called Stein variational gradient descent, does this. So it uses capital N particles, and at each time, each of these particle I is pushed from its previous position, minus gamma, the step size, a gradient that is evaluated at other particles, weighted by a kernel, and there is some repulsive force, also depending on the kernel, between particles. And you can think of, for instance, taking a Gaussian kernel. And here below, it's a screenshot of implementing this algorithm. So here I've taken a screenshot. It's not at stationarity. It did not converge yet, but you can see that particles are pushed from all the space to the target distribution. And hopefully, in the end, you hope that the configuration of particles covers well the target distribution. Okay, so this is for sampling in general, and I've reintroduced famous methods. But in this work, we were interested both in unconstrained sampling, but also constrained sampling. So in constrained sampling, the goal is to approximate still a target probability distribution with some density, but that is defined on a set X that is not necessarily the whole space. So we'll consider a set X that are closed, convex, full dimensional. And there are several applications for that. For instance, you may want to encode some norm constraints on the parameters of your model. For instance, maybe I've given the example of learning the Bayesian posterior distribution on the parameters of my model, the weights of the neural network, for instance. Maybe I want these weights to have some norm constraint. Okay, so in Bayesian lasso, that's the case, for instance. That's one one application where you consider this. Another interesting application that came out relatively recently in machine learning is to encode, for instance, fairness constraints. So this can be encoded as inequality constraints, so space X that is encoded as an inequality with respect to some function G. For instance, you may want that the final prediction of your model, right? I've talked about the Bayesian model average. Maybe you want that your model is fair in the sense that if you feed the model with characteristics and you don't want the model to be sensitive to specific characteristics such as gender, that's one way to encode this. So I will give, in the end of the talk, a concrete example of Bayesian inference with constraints, and in particular, fairness constraints. So once again, feel free to interrupt me at any time. Okay, so if you want to do constraint sampling, there were some methods, so Bayesian methods adapted to this setting. One naive way to do constraint sampling is to say, okay, I will use a general classical sampling method, and I will just reject the samples, the iterates of my algorithm that violate the constraint set. So you can do this, of course. The problem is that it becomes very quickly completely computationally inefficient, and you may reject a lot of samples. So you may run your algorithm for really a long time with a lot of waste. Other methods were improved, such as Hamiltonian Monte Carlo, to take into account the constraint set, but they rely on very expensive subroutines at each iteration, so they are not widely used in practice. So if we take a step back and think about, okay, I want to do sampling with constraints, but I have some, so I want to encode some constraints. Maybe I can look on what has been done on the side of optimization. On the side of optimization, there are a lot of methods that were developed to take into account this. So think, for instance, as a generic problem in optimization, you want to minimize the function v under the constraint that small x belongs to a set x. So what you could do is to do projected gradient descent, for instance, if you have access to a Euclidean projection on x. Okay, so projected gradient descent would run gradient descent and then on the function g, and then compose it with the projection step. So this idea, that is relatively simple, has already been proposed for Langevin Monte Carlo, okay, in this paper, that is relatively recent as well. So you can run Langevin Monte Carlo with a projection step. One issue with that scheme is that you may have particles that accumulate at the border of your constraint set. A second, maybe a generalization of this idea of projective gradient descent is to use another geometry encoded by what is called Bregman divergences or a Bregman potential phi. So a Bregman potential is simply a strictly convex function from the constraint set to R. If you take phi to be the squared Euclidean norm, you will recover gradient descent with what I will describe below, but this is more general. And gradient phi is a bijection from the constraint set to RD. So you can write a mirror descent scheme that writes as follows. So what it does is that it takes the particle xm, it maps it through the gradient of phi, it does the gradient, so it maps it to the dual, it does the gradient step there, and then you need to revert this iteration with gradient phi minus 1 to recover the next iterate. Okay, and the famous example is to choose, for instance, if you want to optimize over R plus D, to take phi that is the negative entropy, so the sum of xi log xi. Okay, so this idea that comes from optimization has already been adapted to both Langevin Monte Carlo and to Stein variational gradient descent in these two papers from 2 and 1 year ago. Okay, so you can write a similar iteration for Langevin Monte Carlo, where the Gaussian noise is rescaled by the Hessian of phi, okay, to take into account this change of geometry. And similarly, you can adapt the Stein variational gradient descent for this. Okay, so I would, to the best of my knowledge, taking into account constraints in sampling is still relatively recent, and at least we see for these algorithms. So one maybe bad side of mirror schemes such as Langevin Monte Carlo and Stein variational gradient descent. So it has been described quite a lot in these papers. Sometimes the updates are still quite expensive due to, for instance, this scaling of the Gaussian noise. And also it requires an explicit formula for the mirror function that describe explicitly your constraint set. So for each constraint set, you should pick the right mirror Bregman potential, let's say. And once again, in the experiment section, in the end, I will show that the choice of the mirror map of the phi really is really important in the final output of the algorithm. So in this work, what we wanted is to develop a relatively simple method for first order. So first order method, just taking into account the gradient of V, that can deal with various type of constraints. And actually, we'll be able to handle these types of constraints. So either X is relatively simple and can be just encoded through reparameterization. So a map F from the constraint set to RD. To basically go back to the unconstrained sampling case. We can also take into account the knowledge of mirror map. I'll show how. And we can also take into account inequality constraints. So to present this algorithm, the idea, as you will see, is relatively simple. And for this, I need to introduce what we call modified interaction energy. So it's the energy that we will optimize to this goal. So since the energy is called modified interaction energy, I need to introduce what is a modifier. So modifiers, so it's a common object in the PD literature. I would say that in machine learning, we will call it kernels, but it's basically this. You take a family of smooth functions phi epsilon, indexed by some epsilon, applying some properties so that positive, symmetric, integrating to 1 with vanishing tails. And you can think of, for instance, Gaussian modifiers. That's the first bullet point, where you take exponential minus square. You can think of Laplace modifiers. So you remove the square. It has heavier tails. Or you can think of Hirsch modifiers, where there is a smoothness index S here. Okay, and as epsilon goes to 0, you go from left to right here. You approximate more and more a Dirac. And what these modifiers do is, so first, as I've said, when epsilon goes to 0, phi epsilon, the modifier approaches the Dirac at 0. If you convolve a function with a modifier, it will smooth it. And you have a pointwise and LP convergence of the modified function. Okay, and what we propose here is to use modifiers to construct an interaction energy that will approximate the chi-square divergence. So I recall what is the definition of the chi-square divergence. It's a divergence between probability distributions defined as follows. So the chi-square between mu and mu star is the integral of the ratio of random Nicodim densities between mu and mu star minus 1 squared with respect to d mu star, if mu is absolutely continuous with respect to mu star, and otherwise it's plus infinity. So it's a relatively well-known divergence that is that dominates the Kullback-Leibler one. And as you can see, it's only defined when mu is absolutely, it's only finite when mu is absolutely continuous with respect to mu star. So that is actually a problem when you want to approximate mu star with a discrete measure. So what we did is to, I will present on the next slide, to propose a proxy for this divergence. So this is the most important slide of the talk. So this is the energy we introduced that we call a modified interaction energy. And it's defined as follows. You pick a family of modifiers indexed by epsilon. You define what we call the modified kernel. So it's a function from RD times RD to R plus. That is defined as follows. So W epsilon xy is the ratio between the modifier phi epsilon evaluated at x minus y divided by the square root of the product of the target density mu star at x and at y. Okay, so this is a kernel, somehow encoding some similarity between x and x star and y, sorry. And from this kernel, we define the modified interaction energy. So that is an energy defined on probability measures on x. That is simply the double integral of this kernel with respect to mu. Okay, so for any distribution mu, any candidate, I can evaluate this energy. Okay, what is nice is that as it's a double integral, mu could be discrete, and this is evaluated in closed form. And so this is the energy we'll optimize and to do sampling. Why intuitively can we see it's already a good energy, a good loss function, I would say. So first, to minimize E epsilon with respect to mu, you want to minimize what is inside the integral, so you want to minimize this kernel. This kernel is the ratio between phi epsilon, the modifier, okay, and this modifier, as x and y gets further apart, it's decreasing. So this says that you want basically particles to be far from each other. This is a repulsive force in the loss. But on the other hand, the kernel is proportional to the inverse of the target density for each particle. So it means that you want mu star of x and mu star of y to be big. So you want to put particles in high probability regions of mu star. Okay, so this is the attractive force. So in the end, minimizing this loss, basically it will drive particles to the high probability regions of mu star. Okay, you want to be near the modes, for instance. But you also want particles to not collapse and to be reasonably far apart. Okay, so yeah, I'm mentioning that here we introduce a loss that is very close to another approximation of the chi-square with modifiers that was introduced in a very recent article, but there is a slight difference between the definition of their energy and ours. Okay, so this energy actually converges to the chi-square. Maybe it's not trivial from the definition on the slide before, but we can see it with very simple computations. So the first proposition here is to say that pointwise, we have convergence of the energy, E epsilon of mu, to the chi-square of mu with respect to mu star, up to an additive constant, as epsilon goes to 0. And to see this, you just have to write the formulas, and it's 2 lines of computations. E epsilon of mu, I recall, is this interaction energy, so a double integral with respect to mu, of the kernel that we have defined. And you can rewrite this as this function, mu divided by square root of mu star, convolved with the modifier, times itself. Okay, so we can write this as this last right-hand side term, where it's the integral of phi epsilon g times g. On the other hand, if you write what is the chi-square between mu and mu star, okay, so it's the integral of this ratio of densities minus 1 squared with respect to mu star. And this, with some basic computations, you can write it as the integral of the same function g squared. So you can already see from here that if epsilon goes to 0, phi epsilon convolves with g converges to g, and so we'll recover g squared above. So we'll have equality. So, yeah, sorry. So this is the first result. So we see that pointwise, we have convergence between the modified energy we propose and chi-square. But to go further, so the pointwise convergence, it tells you nothing about the minimizers of the function, the energy you have defined. And to prove convergence of minimizers, you need another notion of convergence that is stronger, that is called gamma convergence. So this is what we proved here as well. So gamma convergence helps for this convergence of minimizers. And what it says, so I've put the definition here. I won't go into many details, but it says that if you have a sequence of functionals, like a family of proxies, let's say, indexed by epsilon, it will be, so it will gamma converge to a limit functional f if you have these two properties satisfied. So for any mu, you take a weakly converging sequence mu epsilon to mu, and you have this inequality relating the lim inf of the approximate family to the limiting functional. And for any mu, you can find there exists at least one weakly converging sequence such that you have the reverse inequality. So if you have this, you can say that f is the gamma limit of the family of functionals that you're considering. And we prove this for our functional, E epsilon, okay, that is indexed by some small epsilon. So this is what is said here. We take a kernel and we define our modified interaction energy. We can prove that it gamma converges to the chi-square, okay? As epsilon goes to 0, we recover the right gamma limit. And in particular, once you have gamma limits and you assume some compactness, which is what we do here, we have the convergence of minimizers. That is, if we denote mu epsilon star, the minimizers of the modified interaction energy that we introduced, mu epsilon star converges to mu star. Okay, so that says that if you want to minimize the chi-square, the loss that we propose is a good candidate because as epsilon goes to 0, minimizing the loss we propose would recover mu star. Okay, so I hope everything is clear, but feel free to interrupt. So once you have defined the energy, it's natural, since we want to optimize it, to consider gradient flows. And actually, the gradient flow of this energy can be simply written and simply implemented through an ODE in RD. Okay, so where you look at the evolution of a particle in RD, whose gradient flow is described by this vector field W epsilon. And this vector field is simply, so it's the Wasserstein gradient of the loss that we have introduced. It has an explicit form. And you can see here, so there is a typo, it should be a mu t, because it depends on time. This vector field, since there is a convolution with the modifier, it can be written for mu that is discrete. Okay, so it will be easily discretized in space. So this is what I say here. If you want to compute the gradient flow of the loss we propose, it's relatively easy to discretize it both in time. Okay, you have no DE, you can consider Euler discretization, and in space, since we have a convolution, mu can be discrete. Okay, so you can consider a system of interacting particles. So just as a remark, and I'm really open to any comment here. We thought that this was really interesting because we've looked a bit in the literature, actually more than a bit, but we've looked for other ways to implement the gradient flow of the true chi-square divergence. And it seems that there is no way to easily implement it through a SDE, or easily discretize the ODE. So the only reference I found is this paper, and I also asked one of the authors if he had other references, and he did not. So you can write actually a diffusion implementing the chi-square divergence gradient flow, but this diffusion is really hard to implement in practice for different reasons that I can comment a bit later. And this is really in contrast with the Langevin diffusion that I've mentioned earlier in the talk, that you can implement Langevin Monte Carlo. That's a discretization of the Langevin diffusion. That is the gradient flow of the Kullback-Leibler divergence. So here there is a bit of a gap where, in general, it's not easy to implement the gradient flow of the chi-square. And what we have proposed is a way to implement a gradient flow of a functional that is close to the chi-square. Okay, and this is interesting as well because the chi-square has very interesting properties. So this is something that we've seen in practice. It's actually nice to optimize the chi-square. And also on the theoretical side, it's known to have good properties. For instance, if the target mu star satisfies the Poincare inequality, you have linear convergence of the gradient flow, of the chi-square gradient flow. Okay, so this is a nice, at least an interesting object to focus on, from my point of view at least. Okay, other things that we tried to show, but I would say it's unfinished work on that side. So the chi-square functional, so the chi-square between mu and mu star, when mu star is log concave, so that is proportional to e exponential minus v with v convex, it's known to be convex in the Wasserstein geometry. That is the one involved here. Okay, and here we introduce an object, e epsilon, so this modified chi-square, that is not exactly the chi-square for epsilon different than 0. And our intuition is that considering this proxy, we lose a bit of convexity, but we gain some smoothness. We can prove that the gradient is Lipschitz, which is not the case for the chi-square. And we tried to prove some stuff, such as, for instance, that E epsilon would recover the convexity for mu star that is log concave as epsilon goes to 0. And the only thing we managed to do is to prove that we recover convexity as epsilon goes to 0, but only at mu star. So this is the comment I do here. I think there is it's possible to do it, but we struggled with the computations. Okay. So what we managed to prove that cannot be proved for the chi-square because the chi-square is not smooth is the following. If you consider only the time discretization, okay, you can write the following iterates on the space of probability distributions. So you write that the distribution at time m plus 1 is the distribution at time m pushed by this gradient step. So this is identity minus gamma, the vector field corresponding to the gradient of the loss. So this scheme for a step size that is smaller than some smoothness constant decreases our loss at each iteration. Okay, so this is a typical result that you can obtain in non-convex optimization, right? When the step size is smaller than the smoothness constant, we decrease at each iteration proportionally to the square norm of the gradient. And here, the smoothness constant, I'm hiding a bit the assumptions that are here. We need quite a lot of technical assumptions, such as the lower bound on the target density, this kind of stuff. But we can prove that it's decreasing. And as I said, once again, typically you cannot do this for the chi-square because it's known, and I can justify it, that the chi-square is not smooth. Okay, so how much time do I have? Let me see the. Sorry. How much time do I have still, please?
About 15 minutes.
15, okay, perfect. Okay, so now I will talk a bit about the practical side of what we propose. So I've said that we have an energy E epsilon, okay, that you can compute for any mu, in particular mu that is discrete, okay, mu supported on a set of atoms x1 to xn. So we can write this loss. So this is just the discrete version 1. It's the double sum over all the positions of the particles. And the simplest version of the algorithm that we propose is just to do gradient descent on that loss. Okay, so it cannot be more simple. And we've seen that as n goes to infinity and as epsilon goes to 0, minimizing this loss should require mu star. Okay, but maybe here you should notice that this loss requires the target density mu star. And I've said at the beginning that we had in mind Bayesian inference applications where we don't know the density mu star, but only the unnormalized density. So this is not an issue. So when you don't have access to normalizing constants, you can just basically take the log of the energy. Okay, so this is actually helping also for numerical reasons. But we, on the one hand, it's helping, and on the other hand, for very small values, we needed to stabilize the algorithm using what is called the log sum X trick. So here, when you take the log of the energy, you have the log of the double sum. And I had before just phi epsilon mu star. Here, we needed to do this X log, right? So this is helping on the numerical side when you have a very small values for the loss. And this is the true loss we optimize. Okay. Now, this is to do unconstrained sampling. You just do gradient descent on the loss. And I've said in the beginning as well that we are also interested in handling constraints. And for instance, when your target distribution mu star is defined on a set X that is not the whole space RD. There are a few cases. If you are in the simple case that X is just can be encoded by a reparametrization F, basically what you can do is to replace the position of the particle xi with f of xi, and you optimize the loss at the positions f of xi. And this gives you the final positions of the particle. So I will show an example where we have such an access to simple reparametrization. The other case I've mentioned as well is a case where the set is encoded by inequality constraints. What we have done here is to adapt actually another paper by Kyung Liu that we'll talk a bit later today. We use their method that was introduced 2 years ago that is called the dynamic barrier gradient descent. And it's a smart method to basically do gradient descent with constraints. And what it does is that you update the position of the particles, not with the true gradient of the loss, that would be this guy, nabla E, but with a direction vi star, solving this sub-optimization problem. Basically, that says that it should be close to the true gradient, but taking into account the constraint set encoded by the function g. Okay, and this is a very efficient numerical algorithm that was really satisfying in practice. Okay, so let me show some examples. First, in the unconstrained case, we optimize our loss to approximate a Gaussian. So this is MIED is our modified interaction energy descent. So it provides us this approximation. This is IID samples from mu star. This is what is output by SVGD. And this is what is output by a previous method that is called KSD descent. So KSD descent already struggles on this simple case. Okay. Another unconstrained example is that one. So it's a product of two students' distribution. So it has heavier tails than Gaussian. And here we can see that, for instance, Stein variational gradient descent was really struggling with the tails of the distribution, whereas our method manages to put particles in the tails. It's still not that clear to me why it performs better, but I've been discussing with my co-authors. So SVGD, somehow it optimizes the Kullback-Leibler divergence. MIED, our method, it rather optimizes the chi-square. And the chi-square might be better for distributions with heavier tails. That's roughly our intuition. But once again, I'm very open to discuss this. Okay, and now let's look at some examples of constraint sampling. So here, we wanted to do constraint sampling in a box, okay, two-dimensional example. And all these figures are the output of different sampling algorithms, among which Stein variational gradient descent with different kernel bandwidths, KSD descent. This SVMD is the mirror version of Stein variational gradient descent. This is another one because there are two versions. This LMC is the mirror version of Langevin Monte Carlo. And the last 4 boxes are the output of our algorithm with different modifiers. Okay, different modifiers here. And actually with different ways as well to encode the constraints. So I've said that if we have access to reparametrization, that is the case for the uniform box, you can use F that is a hyperbolic tangent. It will map your points in the right space. So in this case, we just optimize our energy with the reparametrization. Okay, and it gives us these 3 outputs. Maybe what I didn't comment enough now that I say is that we can also run our method with the mirror map. Okay, you just do gradient descent, but instead of using the Euclidean geometry, you optimize with respect to a Bregman divergence. Okay, and for this constraint set, you can use that mirror map that is on the bottom of my screen. Okay, so our method is flexible in this setting that we can use actually both tools. So we were relatively satisfied with this because so as we see the configuration of the particles are really relatively well spread on all the constraint sets. Whereas other methods, for instance, here at SVGD, we can see it struggles a bit putting particles near the borders of the constraint set. Something that I've said as well is that all these mirror Langevin, mirror Stein variational gradient descent can only be implemented through, through the choice of a mirror map. And I've said a bit earlier that depending on the choice of the mirror map, it may differ, the output of the algorithm. And that's something that we see here. For instance, for the same constraint, we could have chosen another mirror map, that is that one. Okay, so I'm coming back. It's a bit different from the one on the below slide here. With another mirror map, you may have very poor performance of these algorithms. So here, for instance, we show it for mirror Stein variational gradient descent, where we see that, basically the Stein variational gradient descent performs very badly. And our method, it performs less well than on the slide before, right? We see that particles are more concentrated at the center, but still it's less sensitive to the choice of the mirror map. So this is also something that we were quite satisfied about. All right, so I show some other fun examples of sampling with constraints. So here it's sampling on the 3-dimensional sphere. Okay, so still with our method, different choices of parameters, such as the choice of the kernel, the smoothness index of the kernel. This example is fun as well because here we want to sample from this box, right, -1, 1 squared, still in 2D, but on the set encoded by this inequality here. Okay, and here we plot the evolution of the algorithm along iterations. And we can see that it manages to recover the constraint set. So that's the final output where maybe we have a bit of particles still concentrated near the initialization, but we managed to cover the whole constraint set. And yes, maybe last but not least, I promised as well at the beginning an example of of sampling with constraints, where we have a constraint set encoded by inequality. Okay, so I've shown an example on the slide before, but here it's a practical example where the inequality enables to encode fairness constraints on a model in machine learning. So the example is the following. Assume you have a data set D, okay, of Wi, Yi, Zi. Okay, so you have features, for instance, on individuals, Wi, of some gender, it's a man or a woman, and you have a label Yi. Typically here, the label is saying whether the individual has a high income, okay? And you want to be able to predict, given the data Wi, and if, sorry, I found something. Okay, if you want to predict the label Yi, okay, but you want the model to be not too correlated with the sensitive attribute. You want to predict in the same way for a woman or for a man. Okay, so here the target density, the mu star, is the posterior, the Bayesian posterior of a logistic regression using Bayesian neural network for the prediction Y hat, and the inequality constraint on the parameters of the Bayesian neural network is encoded this way. We want to sample parameters on the network such that the function g evaluated on the parameters is negative, and this function g basically encodes the correlation between the prediction of the model Y hat given an input W and the parameter X with the sensitive attribute. Basically, you don't want the parameter prediction, the model prediction to be too correlated with the sensitive attribute. Okay, so this is the setting. We basically run gradient descent with the dynamic barrier method for solving this task. And what is nice is can be seen on this graph here, is that our method, the blue one, manages to really find a good trade-off between fairness and accuracy. Okay, in the sense that basically you can attain the best accuracy, have the best predictions, fitting your model without taking into account constraints, at the price of no fairness. Okay, so you would be here on the graph, and demographic parity that encodes the fairness would be very low. On the other hand, if you enforce some fairness, okay, you force the parameters to be not correlated or less correlated to the sensitive attribute, you may lose some accuracy, right? Your predictions are less good, but you are more fair. And this is the other extreme of the graph. And other methods do not manage at all to recover this Pareto front. Okay. So to conclude, so we tried to tackle the problem of sampling, in particular on constrained domains. It's a challenging problem. The state of the art is still, I would say, evolving and still has a lot of challenges to tackle computationally and the kind of constraints it can handle. And here we provided a relatively simple method that is flexible on the type of constraints and is computationally friendly. We have a GitHub to reproduce our experiments if you want to try it, with also Stein variational gradient descent and other baselines. There are still quite a lot of open questions. For instance, it might be interesting to reduce the bias that we have coming from the fact that we have an epsilon parameter that is strictly positive. All right, I've said that for a fixed epsilon, we recover a mu star epsilon that is approximately mu star, but that is different. And maybe we can borrow ideas, for instance, as in entropic optimal transport, where people have proposed sin-corn divergences to debias entropic optimal transport. That is also biased thanks to parameter epsilon. So that could be an interesting way to do it. And also, we have guarantees on the optimization side, right? I've said that we know that we decrease our loss at each iteration, but we don't have any guarantees on the quantization properties of the output of the algorithm. Okay, so maybe, and for this, so this is an open question, can we get an upper bound on the minimizer, let's say μn, for n particles, on the loss that we obtain, depending on the number of particles and mu star? So yeah, I'm done, and thank you for listening, and I'm happy to take questions.
Thank you, Anna. Any questions from the audience?
Thanks for the talk. And I was wondering if you thought that this kind of robustness to bad mirror maps was general. And if it is general, could you give some intuition as to what it's robust in this way?
So I don't hear very, very well. I've heard it was about the robustness to the choice of the mirror map.
Yes.
And I don't know if the question is whether I have an intuition on why we would be more robust.
Yeah, that's the question, exactly.
Okay. That's a very good question. I'm trying to think. Yeah, I'm not that sure. I don't want to have a bad intuitions. Actually, so one thing I could say, but I don't know if it's explaining this or not. So the choice of the Bregman divergence, hence the mirror map, is heavily related to the objective function that you use, right? So, for instance, Shine versional gradient descent, these two algorithms, they are optimizing the Kullback-Leibler divergence, and here we are optimizing something that resembles the chi-square. And in one way, you could see it as KL optimized with the mirror map, and on the other hand, chi-square optimized with this mirror map. So maybe our objective is better for a larger set of mirror maps. But I'm not really sure about that explanation, but yeah, it's known in optimization that you can, if you choose well the mirror map, for instance, if your objective is smooth and convex with respect to the mirror map you choose, you can have good convergence properties. So maybe that's one way to think about it. The interplay between the mirror map and the objective is not the same for other algorithms and ours because we don't use the same objective function. But yeah, it's a good question.
We're running a little bit behind, so maybe just one final question. Sorry, go ahead.
So how do you choose a bandwidth for the modified kernel?
Did you hear the question?
How do you choose a bandwidth? Is it fixed or the?
We fix it during the algorithm, but once again, it's a good question. So typically, I didn't put the numbers here each time, but it's depending on the number of particles. If I remember well, so we fix it very small actually. I think here on this example, it's in the paper, but like epsilon is n to the -8 or something like this. It's really, really small with respect to n, the number of particles. So yeah, at the price of some other numerical tricks that we had to do, because when epsilon is very small, that's something I didn't comment here, but we use, yeah, maybe put it here. For very small epsilon, we had to rescale diagonal term of the loss because they were really dominating the others, and it was not good for optimization. So to answer briefly to your question, we don't have a fixed rule to fix the epsilon. In practice, we fix it with respect to the number of particles, but we still can take it very, very small. And we managed to optimize our loss for very small epsilons, and still have stable optimization, basically.
Okay, can we thank Anna again, please?
Thank you.
before we go for lunch, are you able to change the slide for the AGM? We'll have to do it here.
You pick one up. Should all be on there.
So before we go for lunch, I'm just going to keep you for a couple more minutes. I apologize. So today's workshop was organized by the Computational Stats Machine Learning section of the RSS. And each year, we are, by RSS rules, required to run an annual general meeting, which is going to take 2 minutes of your time, but we do need people to be here. Otherwise, it'd be like it was last year, with just me and Ben on a Zoom call talking to each other. So
We need to share it on Teams. We need to share it on Teams as well, because I won't be able to see it online. That's it, perfect.
great. So I'm Chris Nemeth. I'm the current chair of the section until the end of this month, and I'll be new chair. And this is only going to take a few minutes, but I just want to recap on the activities of our section for this year. So obviously there's a workshop that we're having today, part of our activities. But the biggest activity that our section has undertaken this year has probably been the series of discussion papers that appeared in Series B, or will soon appear in Series B, on probabilistic and statistical aspects of machine learning. One of those papers on diffusion generative models is actually quite related to the topic of today's workshop. We also ran a session at the RSS conference this year in Harrogate on making better use of MCMC samples, which Chris Oates kindly organised. And we've been engaged with the RSS through a few different means, but in particular, there was a discussion meeting at the RSS conference on evaluating AI, and some members of our section took part in that. Okay. So for next year, there'll be a new chair of the committee, which will be Adam Johansson, University of Warwick. Chris Oates will be vice chair, Anthony Overstall from Southampton will be secretary, and Sander van Roy from Bath will be the meeting secretary. The other members you can see there will also be part of the committee next year. Now, this is the part where we'll have to vote on the committee, right? So what we'll do is we ought to have a show of hands to say whether you agree with this committee for next year. So we'll have a ayes and nays. So those who agree that we should have this committee, put your hands up, please. Right? And anyone who disagrees, right, so the ayes have it. The ayes have it. I'm glad you agree, because there's no backup plan if you disagree. So just to sort of like highlight what's going to be happening for activities next year. So thank you. We have a few workshops planned, or you'll see advertised quite soon. So there's going to be a natural language processing workshop sometime early next year, focusing around large language models. That'll probably be here or somewhere else in London. There's also going to be a workshop in Manchester on uncertainty quantification for large language models. That's going to be joint with the Ellis Institute, because you're familiar with Ellis. Reinforcement learning workshop later in the year, organised at the University of Bath with the Bath local group. And potentially, if it's accepted, we propose some sessions for the RSS conference, which takes place next year in Brighton. Chris Oates and a few of his collaborators are all organising a summer school on probabilistic numerics, which is going to be happening in sort of Southampton around about early April. And we're also welcome to suggestions. So if you have any ideas for things you might want us to organise next year, well, not me, I'm not here, but you can talk to somebody else. Suggestions for next year, then we're quite welcome to hear those. And that is it, I think. That's my last slide. Yes, so you're all free to go and enjoy lunch, and then we're reconvening at about 2 o'clock. Thank you.
So the common solution to this type of problem is choose a Q that minimizes a discrepancy between P and the Q. For example, KL divergence between P and Q. Right? There are many ways to minimize the Kubeck-Leibler divergence, but since, for example, doing the gradient descent in the parametric space, or maximizing the elbow for variational inference, right? But since you are coming here today in the gradient flow workshop, I suppose you're interested in this kind of gradient flow way of minimizing the Kubeck-Leibler divergence. I suppose you're all very familiar with gradient flow already, but let me just rephrase this kind of statistical procedure using our notation, so it is easier for us to discuss later. So first of all, what is gradient flow? Imagine a curve in probability space Qt, and T is a continuous time index along continuous time index from 0 to infinity. And you can think along such a curved trajectory, Kullback-Leibler divergence reduces gradually, right? So I start from something with large Kullback-Leibler divergence between P and the Q, and then I move the probability measure of Q over the time T. Then in the end, I gradually reduce the size of Kullback-Leibler divergence, right? So this is the kind of curve in the probability space. It is characterized by an ordinary differential equation. For example, partial TQT equals to VT. Okay, this is very easy to imagine, right? Just imagine a curve in the space, and then along the curve, you reduce the Kullback-Leibler divergence. But it is not very easy to compute. As a matter of fact, in order to compute this gradient flow, it's much easier to do the same thing, but in sample space, right? So let's represent the distribution P and Q using their respective samples or particles, okay? Suppose, xt are samples from distribution Qt, then you can see that gradient flow also specifies a particle evolution from Q0 to Q infinity. When T is large, we can see that the particles gradually evolve over time to approximate our target distribution P, right? So that is the particle evolution ODE also specified by the gradient flow, okay? And their relationship, I forgot to mention here, but their relationship is also characterized by the Fock-Planck equation. So the particle evolution and the curve in the probability space, the same thing, okay? And you can easily see why gradient flow in the sample space is easier and more attractive, because I can directly modify my samples in the sample space, right? I don't need any model. I don't need any generator. I can just update my particles over time, and then eventually I will get something that approximates the true target distribution P, right? Really nice. So this has been really popular in machine learning communities now. Okay, so let's have a look at a specific example. We mentioned the Kullback-Leibler divergence before, and in fact, the evolution ODE, particle evolution ODE for Kullback-Leibler between P and the Qt can be written as follows. So basically, the evolution is characterized by the gradient of the density ratio function between P and Qt. And what about the gradient flow of other divergence, right? So in the talk, we only focus on F divergence. There are many other discrepancies, but we only focus on F divergences. So we have seen the example for Kullback-Leibler. What about other divergences? In fact, there is a general form available. Suppose that F divergence is defined in this way, which is expectation with respect to Qt. F is your choice of F function in F divergence, and then it is a function of the ratio RT, and the ratio function is just the P, the target, divided by density Qt, right? If your F divergence is expressed in this way, then the particle evolution ODE takes this general form, which is nabla x HR of x, okay? And this H function is a function of ratio P divided by Qt, and can be written in this way: R times F prime minus F. F prime means the derivative. Okay, and there are many previous work already pointing it out. And this exact form is what Mingxuan did in his paper, and I find it's really nice to work with. But previous work also have very similar results. Okay, so we can see a few examples of different F divergences and their particle evolution ODEs. And here we have Kullback-Leibler, and the F is F R times log RT. And then here the HR function, which is the HR function here in my particle evolution ODE, is just R, just the density ratio. right? And the reverse KL is KL between Q and P. Then the F here is minus log R, and then the HR function is -1 plus log R. So it is HR function is actually the logarithm of the ratio between P and QT. And also I derived for Pearson chi-squared divergence. And in this case, F is just the quadratic form of ratio -1, and then HR function equals to R squared divided by 2 minus half. Okay, so you can go on, derive a lot of different gradient flows for different F divergences. And not only this kind of gradient flow of F divergence is very kind of interesting, theoretically interesting, but it's also practical because you can actually simulate them using discrete time algorithms like gradient descent. So for example, variational gradient descent. All you need to do is just sample x0 from some kind of initial distribution q0, and then you just update the particles according to this nabla of HR function I mentioned earlier. That is my particle evolution ODE, right? And then I have a discrete simulation for the continuous time ODE. And when t goes large, then I can think that qt approximately equals to my particle target distribution t. Okay, so here is just a visualization. I had a continuous time curve, but now I try to discretize it every time with a discrete time simulation algorithm like gradient descent. Okay. Okay, so the end of the talk, right? Let's go home and minimize divergences, because this is, practical. This is easy to do just using gradient descent, right? But not so easy, because the gradient flow ODE I was talking about, nabla HR, it is a function of ratio RT, and this ratio RT is ratio between P, the target density, divided by QT, the particle density function. And if we know P and QT, then we can compute RT. And then this H function I can also compute easily. Then there is no problem. We can just do this gradient flow. However, it's unlikely that we know the exact density function of QT, because QT arises from complex particle dynamics. And also in generative models, we don't even have information about, we don't even have density function of P. We just have samples from a target distribution, right? We want to generate samples that similar to human faces. Then I only have images of real human faces. I don't even have density function of human faces. And therefore, computing this nabla HR is in general intractable. Therefore, this is the main quest of this talk. So what can we do to solve this issue? How do we approximate this particle evolution ODE nabla HR? So there exists a simple solution. This has been adopted by previous works, and apologize here, I actually forgot to cite some previous works. But in fact, this H is a function of ratio, and ratio can be approximated using density ratio estimation. And this is a technique I think nowadays widely known in machine learning community, thanks for GANs. And this density ratio estimation just approximate the ratio by R hat, right? And then I just approximate the particle evolution ODE using the nabla of HR hat, the estimation, the plug-in estimation of the ratio, and then I just differentiate the whole thing. In reality, my ratio might be a neural network, therefore I just use automatic differentiation for such a job, right? But wait a second, right? Am I talking about this nabla HR approximated by nabla HR hat? That is replacing R with the estimated ratio. So does that mean I'm saying a good density ratio estimation is approximately a good gradient flow estimation, right? Let's have a look at an example where the good density ratio estimation does not guarantee a good gradient flow estimation. Imagine the simplest case, Kubeck library divergence, whose particle evolution ODE is just there, the nabla of the ratio, right? and consider this least square objective function for evaluating the density ratio model. And in fact, it is just a least square loss between the true density ratio and the density ratio model. And it actually is a legitimate density ratio estimator called unconstrained least square importance fitting proposed by Kanamoli 2009. Okay, so let's have a look. Under this density ratio estimation criteria, how does different density ratio estimation is chosen? So suppose I have a true density ratio that is green, that is blue line. I have the red line, which is one density ratio estimate. I have the green line, which is another density ratio estimate. And you can see that the red line kind of very, similar to the blue line in terms of the proximity. Therefore, you can see this least square objective will favor the red model than the green model, okay? And because of the proximity of the red line to the actual density ratio, right? However, if you look at the gradient of these two density ratio models, and the red density ratio model is just fluctuating all over the place, right? Because a little fluctuation in your density ratio estimate will result in huge fluctuation in the gradient, and this is reflected by this kind of very wiggly shape of the density ratio. The gradient plot. In comparison, my green density ratio model is more stable, at least comparing to this red density ratio gradient. This green density ratio gradient get the sign correct, right? So at least I have negative derivative smaller than 0. I have positive derivative that is big when x is bigger than 0. So at least the green density ratio estimate get the gradient signs correctly. Okay, but unfortunately, the least square objective will prefer the red model to the green model because of the proximity. And this kind of fluctuation happens a lot in density ratio fitting because of overfitting, right? You use a neural network, you overfit, and then the model becomes very fluctuating. So here is a kind of a warning that good density ratio estimate does not guarantee a good gradient flow estimate. Okay, so what should we do now? How should we get good gradient flow estimate? So what I'm going to talk about is gradient flow estimate using the Nadaria-Watson estimate. So let's first set the problem. Suppose I want to estimate this gradient flow, right? Nabla of HR. And specifically, I want to have a good local approximation of this gradient flow ODE that is evaluated at x equals to x0, where x0 is a fixed point. It's not something random, it is a fixed point. And then what should we do? Actually, in this case, we want a local approximation of the gradient flow, and we naturally tend to look at some local approximation methods. For example, Nadaria-Watson approximation or Nadaria-Watson interpolation. And Nadaria-Watson interpolation for a function g at a fixed point x0 is very simple. Just sum over the function evaluations at different x point, right? Then weight them by a kernel function k at those points. And then this kernel function is also evaluated at x0. So basically just a bunch of weighted sum of function evaluation. And then take the average to approximate the function value at x0. And one thing to note is the kernel used in Nadaria-Watson must be normalized, which means the expectation of the kernel with respect to x must be equals to 1. Okay, so the kernel must be normalized to 1 with respect to x. And then you can prove that the Nadaria-Watson is asymptotically unbiased as the bandwidth shrinks all the way to 0. And you can easily see that just by doing Taylor expansion on the function g, and then under mild assumptions of higher order derivative of g, this bias term will be eliminated as the kernel bandwidth goes to 0. And because of this kernel function is normalized to 1, so this term and this term will just cancel. So the only thing left is just your Taylor expansion terms, and then under mild conditions, those terms reduces to 0. So it is asymptotically unbiased when the bandwidth goes to 0. So the natural idea is, can we just use Nadara-Watson to approximate the KL gradient flow then, right? So it's very simple, right? The Nadara-Watson estimator is just the weighted sum of nabla R of X. And theoretically, it is possible, right? Weighted sum, what is wrong? But in reality, we can't do that because, again, we are confronted by the issue that we do not know the density ratio function R, right? But if imagine that we could do such NW estimation, then you can see our estimator would also be asymptotically unbiased as the kernel bandwidth goes to 0, right? Because the same deal that just expand your density ratio function at x0 using Taylor expansion, and then the bias terms will vanish as the kernel bandwidth goes to 0, right? So in theory, it is a good gradient flow estimation. And let's have a look at another divergence, that is reverse KL divergence. In this case, reverse KL is just the KL QP, not KL PQ. So the particle evolution ODE is nabla logarithm of ratio R, right? And then let's have a look at the expected Nadara-Watson estimator. This expectation is taken with respect to the particle distribution Q. And you can see this nabla of log ratio naturally decomposes into two parts, log P and log Q, right? Because log ratio is just log P minus log Q. And then you get blue term and the red term. And this red term, under mild conditions, can be translated using integration by parts. That looks like this. So basically, the log Q term is gone. Instead, I just have the nabla of the kernel function K, right? And then if we can compute the gradient of, if we can compute the gradient of log P, you can see that this expected Nadara-Watson can be approximated using our samples, right? I just replace this blue term with samples, and then replace the red term here with samples. Then I end up with a Nadara-Watson estimator of the reverse KL gradient flow. All right. So this is something we can actually calculate because the expectation is with respect to Q, our particle distribution. Sorry, how much time do we have?
You have another 22 minutes.
22. I see. Okay. Okay.
No, 17.
17. Okay. Okay. I see now. I see. Don't worry. Don't worry. The good part has passed. So okay. So you can see that this Nadara-Watson estimator, right, has two terms, blue term and red term. But I can combine these two terms and under the single sum, and now I have this kernel times nabla log P plus nabla of K. And this green term is something special because this is just a Stein operator applied on the kernel function K of x0, where the variable is the first argument x here. Okay, so it's just an average of Stein operator applied on some kernel function. It looks very familiar, right? I think you must think that way. Because this is exactly Stein variational gradient descent. It looks exactly like Stein variational gradient descent because Stein variational gradient descent computes the update for a particle x0 using this exactly the average of the Stein operator applied on L, where this L is the kernel of an RKHS, right? However, let me just clarify here. Our Nadara-Watson estimator is not SVGD because the K in our case is normalized, which means that it is not symmetric in general. And in that case, K is not a kernel function in RKHS. So you can see that NW estimation, SVGD look similar, but they are two separate things, right? And indeed, if you do some experiments, and here I just use the NW estimator to to approximate the KL, reverse KL flow. And then I use the SVGD flow here, and I compare the particle trajectory of two different flows. And here on the left, I have SVGD flow. On the right, I have the NW reverse KL flow. And they both use the same step size, same kernel bandwidth, which is the median trip, using the median trip, and run 50 iterations. So you can see on the left that the SVGD seems to converge much slower than the NW reverse KL flow. And the NW reverse KL flow, the particles converge more uniformly, right? You can see after 20 iterations, all the particles have converged to their target locations, while for SVGD, even at the very end of the flow, there are still particles, are not converging to their target positions. Right? Oh, by the way, so the vertical is the space, and the horizontal is time. So it's a space-time plot of particle for both flows. Okay, what about other gradient flows? What if I can't compute nabla of log p, right? So first question is, what about other flows? So I only talked about this Nadaria-Watson for reverse KL flow because it's sort of like a special case where you can, nicely work out this expectation with respect to log q. But what if you don't have that logarithm? How do you estimate that gradient flow? And also, computing SVGD or the NW estimator, we both require nabla of log p. What if you're in the generative setting? You don't have density p, right? How do you estimate gradient flows? Then let me introduce local linear regression method. So local linear regression is another type of interpolation method, very commonly used aside of Nadaria-Watson. And here, the idea is simply approximating a function g using a linear model. And this is literally just a linear model with coefficient beta, where beta hat is computed by minimizing the least square loss, weighted by this kernel function k here. Here, kernel doesn't have to be normalized, but just a minor detail. More interestingly, not only this local linear regression is a good estimation of function value, but it's also a good estimation of the gradient of the function. And in fact, Hasti et al. In the Elements of Statistical Learning, he noted about this, said local linear regression automatically modified the kernel to correct the bias exactly to the first order, right, the gradient, a phenomenon dubbed as automatic kernel carpentry. So not only is estimator is good for estimating function value, but also for estimating the gradient function, which is exactly the thing we want, right? But can we apply, Okay, so the intuition is very simple, right? Because you are fitting, a local linear model, and the gradient is just, the slope of the best local linear fit of your function. Therefore, local linear regression will give you a good gradient estimation. That makes sense. Can we apply this trick to gradient flow estimation? Well, of course, gradient flow estimation is not regression. We don't have output. We don't have input. So we have to find some different loss functions, a loss function that at a minimum, our model is exactly equals to this h of r, right? H of r that appears in the particle evolution ODE. And then once we have the loss, we just localize that loss and obtain a local linear fit. And then we just obtain, take the slope of the local linear fit, which is beta here, as my estimation of the gradient flow, okay? Nabla h of r. And the key is to find the loss. So here is the same plot, but I'm only changing this function g to h of r, which appears in the ODE. And then I approximate it using the local linear fit. Then the slope is going to be my estimate of the gradient flow. So what is the loss function? So to answer this question, we need to introduce a little bit of technical detail called dual divergence. And the dual divergence is defined as a relationship between two divergence. Let's say you have d phi and d per c, denote two F divergences with F equals to phi and F equals to psi respectively. And then we say d psi is the dual of d phi if and only if phi and psi satisfy this relationship. Okay, so that's my definition. And then you can see that chi-square Pearson chi-square is the dual of KLPQ. KLPQ is the dual of KLQP. KLQP is the dual of the Neyman's chi-square. And if you're OCD like me, then you might wonder, is Neyman's chi-square the dual of Pearson's chi-square? The answer is not. Actually, if you keep playing this game, you'll get something different, a different type of F divergence. Okay, so that's the definition of dual. Then you can see, because the dual is an F divergence, then it has a variational expression, right? This is very, very well known in machine learning community. Is the workhorse behind F-GAN, right? So you can rewrite this F divergence using the supreme of EPD minus EQ, the convex conjugate of psi and function of D, where D is a functional. In GAN literature, they call it discriminator, but it's just a functional. Okay, so here is the reason I'm introducing this dual divergence. So it turns out, let this gradient flow, nabla HR, be the gradient flow of d phi, which is not the dual, but original F divergence. Say you want to compute the gradient flow of the d phi. Then the supreme of 1, which is the variational form like this, variational expression this, is attained if and only if dx equals to h of r. So this way, you can see this variational expression is exactly our loss function, right? Because the supreme is attained if and only if when the discriminator d equals to hr, which is the function I want to approximate, right? And then I can just replace the local linear least square regression loss with this kind of loss function, and then do local linear regression to obtain the estimation of the local linear mode, to obtain a local linear fit of the HR function. Okay. So now we have this loss function. It is just EP of D plus EQ psi convex conjugate D. Then we just localize this loss function by introducing a smooth kernel K, right? The same kind of K appeared before in the local least square regression. And then we replace this D, the discriminator, with the linear model, right? And then this is our objective function. Then we just obtain the local linear fit by minimizing this localized objective function. And then this coefficient of the local linear model will be our estimate of the gradient flow, nabla of HR. So I think the key insight here is that in order to find the gradient flow of an F divergence, you need to compute its dual's variational expression. So this is something I find is interesting, and I haven't experienced before. Okay, and you can also derive some theoretical results for our local linear gradient flow regression. And just like local linear least square regression, it is also asymptotically unbiased if the second order derivative of HR is well behaved. And then as the kernel bandwidth reduces to 0, our estimate beta here will be asymptotically unbiased, right? Just like the local least square regression. Okay, so I think I'll skip the hearing. How many time?
6 minutes.
Oh, 6 minutes. Okay, great. Okay, so so here are just two examples: the gradient flow of the Quebec-Labrador divergence and the gradient flow of the reverse KL divergence, right? And in the former case, we have the gradient flow, which is nabla of the ratio, and then what we need to do is just to find the dual divergence of the KL, which is the chi-square divergence. And then we just take the per-c function, find its convex conjugate, which is d squared divided by t plus d. Okay, and then we just replace the per-c con over here with this quadratic function. And you can see this gradient estimation solves a quadratic optimization problem. And this can be solved analytically. And also, for reverse KL divergence, our target is to approximate nabla log R, right, the logarithm of the density ratio. Then we find the dual of the forward KL is, sorry, dual of the backward KL is the forward KL, and then we find the per-c con in the forward KL divergence to be the exponential function d minus 1. Then we can calculate the gradient flow by solving this convex minimization problem. And this can't be solved analytically, but you can easily solve it using some kind of like gradient descent method. Okay. So I just want to maybe quickly go through some experiments. So as I said, it is a preliminary work, so I only have some preliminary results. I apologize for that. So in this case, we want to estimate the gradient of the log density ratio R, and then we draw 5,000 samples from P and the Q, and then we compare our local linear estimator with a neural network estimator of log R, then differentiate using backpropagation. And you can see the comparison here. The red line is our estimator, and the yellow line is the neural network estimator, then automatically differentiated. And you can see the proposed estimator, is more aligned with the ground truth. Okay. And the second experiment is the estimation error. So I compare the estimation error again of the gradient of the log density ratio function and compare it with kernel density estimation and kernel score matching. I compare with these two methods because they are also kernel-based methods, right? So naturally, I wonder what is the performance differences. For kernel density estimation, I just estimate P, estimate Q using KDE, then take the ratio, take the derivative. Then I get the gradient flow. And for kernel score matching, and this is more interesting because this is not a density estimator. It is the estimator of the gradient, right? And so I directly estimate nabla log P, then estimate nabla log Q, then take the difference. That gives me nabla log P divided by Q. Then I compare the performance of these methods over different sample sets. So you can see the proposed estimator gives you the smallest estimation. And I had some animations here, but I couldn't play here. That's all right. So in the final experiment, I test the performance of the gradient flow estimator in a generative modeling task. So in this case, I start from Q0, and then gradually I push particles to approximate my target distribution. And in this case, target distribution is MNIST dataset. And I start from Q0, which is just a normal distribution fitted on MNIST dataset. And then I run gradient flow estimated using our estimator for 100 iterations. And this is a very challenging task because this is a high-dimensional dataset. And we're only using a local estimator with a kernel function. So this is a very challenging for our sort of kernelized estimator. But you can see that although we are using this kernel method, we have improved the quality of generated images by a lot after just 100 iterations for both forward and backward KL flow. Okay, so these are the limited experimental results I have. Right. Okay, so let me conclude. So what we have done is we proposed the interpolation using the Daria-Watson estimator for reverse KL gradient flow, and we say it's asymptotically unbiased as the kernel bandwidth reduces to 0. More generally, we can also approximate any gradient flow using local linear regression, not really a regression, but using the concept of dual divergence. And we also claim that the estimator is asymptotically unbiased as kernel bandwidth goes to 0. and achieves promising results, at least in the limited experiments I have. I suppose I'm finished. Okay, good.
In fact, that was spot on. You weren't late into 1 minute, so which means that we have now 5 minutes for questions. Any questions for Sean?
Yeah, thanks so much. Great talk. I was wondering about the first one with the ambiguity.
Yes.
Like you said, I couldn't really follow. You said, first of all, you said the K has to be normalized.
Right.
And I guess it has to be normalized with respect to Q.
Yes, exactly.
And so when you implement it, do you have to normalize the constant from the Q?
Yes, I have to. Yes. So for each time I approximate the gradient flow, I have to compute the normalizing term using samples from Q.
That like it becomes maybe symmetric. I don't really understand it because like can't I just choose K a Gaussian? Yeah. And then you normalize it the way you like a Gaussian kernel, and then you normalize it the way you do, or it's not possible?
Right. So okay, so I see. So the normalization must be with respect to the density function that you are taking expectation of.
Yeah.
So here I'm taking expectation with respect to Q. So the normalization must be with respect to Q, the data density, the particle density function. So I can't use like normalized, Gaussian kernel with
This I understand. I'm sorry to interrupt. This I understand, but I thought like I thought is it like you fix K, like I write K of X comma Y, like the constant times exponential to the minus, such that it's a Gaussian, and then you estimate the constant, but that's not the way you do it.
So in this case that I simply just approximate this expectation with sample, like 1 over n, like sample average from distribution, using particle from distribution Q. And then that is my approximate normalizing term. Then I just divide my K by that normalizing term. I think this is exactly what you just mentioned.
Yeah. And in this case, wouldn't it be GD more or less exactly, or not?
No, not exactly, because the normalizing term differs for different particles, x0. However, in the SVGD, that the kernel don't normalize at all, like are not normalized. So basically, every kind of particle use the same kernel.
So the normalization constant depends on the x.
Exactly. Okay. Depends on x0. Yeah.
Oh yeah. Okay.
Yeah. Exactly.
Okay. Thanks. Yeah.
Questions? There is an online question. There's an online question. Okay. Saif asks, can you provide some intuition on why you chose your notion of duality compared to the traditional dual F divergence induced equal to the F star divergence, where F star is convex dual?
Yeah, thank you very much for the comment. Actually, I was just having a chat with Heshilo earlier, and we also, so actually, when I was writing this, the slides and also the paper, I wasn't aware, honestly, about the conventional definition of dual divergence. So this is just my way of defining it in the simplest possible way that gives me the result that I want. I don't know if that makes sense or not. Actually, I was just checking earlier, and I think these two dual divergences are closely related and possibly even equivalent. So I haven't investigated along that direction yet, but definitely that's the first thing I'll do after the talk.
Any other questions?
Just to add to the discussion. I think it's a duality between breakdown physics and may not be like the main except for Chanel. I don't know exactly it's a kind of equivalence between these two concepts. But maybe there's something interesting.
I see. Yeah. Thank you very much. Yeah.
And one last question.
Yeah, so SVGD doesn't work well in high dimensions. That's when you have a variance collapse. Just I'm wondering, does that happen for your first algorithm too?
So for example, in the MNIST image data set, it happens for some divergences, for example, like a K forward K, not for the Pearson divergence has the kind of most severe issue of collapsing to like a single mode. Like sometimes just become all ones somehow. I'm not sure if the variance collapsing still happens like in more general sort of divergence settings. But I think maybe the normalizing constant does help a little bit. Kind of you can think this normalizing constant is control the speed of individual particles so that they somehow don't behave too aggressively, or I don't have a theoretical understanding of that. Maybe that could be a reason that maybe it doesn't collapse, but maybe it also does. Okay. Yeah.
Thank you very much. Let's thank so we don't have to be clicking. Okay, so let's start the next talk. That's good, I think. My pleasure to introduce Francesca. She's done her PhD in Warwick and then now in France in Ensai as postdoc? No, postdoc.
Yes,
yes. Postdoc, yes. And then
I'll take my time.
yes, and she's coming back, luckily back to London in January. She's going to start King's College Department of Mathematics. All right, and her talk is about Wasserstein gradient flows for solving integral equations.
Yeah, thank you. Thank you everyone for being here and for giving me the chance to talk about this over here. This is joint work with a couple of people that have already been mentioned today, Valentin, Arnaud, who were based in Oxford at the time, and Adam Janssen, who was my PhD supervisor together with Arnaud. As you can see, this has been out for quite a while, so apologies if you have already seen part of this talk, but there are new stuff as well, which are like preliminary results, so it would be very good to hear some feedback on those too. So, well, the reason why I think I like giving this talk is because gradient flows are a tool that has been used a lot in the sampling community, but it's a tool that comes from a different field. And this is just one way, well, one application, which is not sampling, in which they prove to be quite useful as well. And the application is integral equations, which I'm going to spend a bit of time about because they're not the most well-known application. So yeah, that's the first part. Freedom integral equations are a particular class of integral equations. What I mean by integral equation is this, an object like that one. So I have two sides of the equation, like in any other case, but like I have the integral operator over here, which you can imagine this, the first one, the first kind, to be the extension to infinite dimension of linear systems. So if you think about a linear system, AX equal B, normally you want to find X given A and B. In here, the role of B is fulfilled by the measure mu, and the role of the matrix is fulfilled by the integral with respect to your kernel K. So basically, it's the same object. If you discretize this integral equation by, I don't know, in one dimension, you can think about discretizing your domain, and then just evaluating the function at fixed points, you get exactly a linear system. But because they are infinite dimensional rather than limited to vectors, we're thinking about functions or measures, they are much more powerful and they describe a wide number of phenomena. I mentioned some of them over here, density deconvolution, image reconstruction, which includes image deblurring as well. They arise a lot in connection with PDEs. So like the fact that we don't just consider vector but functions is quite important. The second kind is again written in terms of an integral, and if you forget about the term phi, what's left is very, very similar to an eigenvalue problem. It's actually exactly an eigenvalue problem for the integral operator defined by K. So again, if you discretize these objects, you end up with the standard, I want to compute the eigenvalue and eigenvectors of a matrix. But if you look at it in continuous space, then you're looking at eigenfunctions and not eigenvectors. And well, if we look at it from this perspective, then we can describe a lot of phenomena in this way. Optimal control has some applications in optimal control can be written in this way, and as a consequence, reinforcement learning, because the two are very much related. Light transport satisfies an equation of this sort. So this is a sort of summary of the objects that we have over here. So the kernel K is common to both integral equations, and we assume that it's known analytically. And I would just refer to it as an integral kernel, no specification so far. It could be Markov, but it doesn't have to be. And lambda is a positive, well, is a real number, sorry. Pretty much like any eigenvalue you would think of. Phi is a forcing term, which I will assume to be positive for the remainder of this talk. Mu is a probability measure that we observe. We observe analytically, meaning that we know the density, or through samples. Both of those are okay for what I'm going to talk about. And our task is to recover phi. So I will be focusing on the first kind mostly. So basically what I want to do is to solve a linear system, but in continuous space, pretty much. So when you think about solving a linear system, well, if you're in finite dimension, the first thing that you want to do is just, least squares, pretty much. When you look at this in continuous space, which means looking at measures or functions, this is a very ill-posed problem. It's already quite ill-posed in finite space, but in continuous space is even worse. And I will show in one of the examples how bad it is. So you cannot just, invert the integral kernel because it's not invertible. You cannot do that. In a finite dimensional setting, you can hope to invert the matrix or something which is very close, like the Moore-Penrose inverse. With kernels, you cannot do that at all. So you need something different. Something different normally means defining divergence between the left and the right-hand side of the equation and adding a regularizing term, which is what we have over here. So what sort of different divergence can you pick? Well, we chose the Kullback-Leibler for reasons that will become apparent in a bit. You could also pick the L2 distance, and this would lead to a slightly different algorithm, but which has the same spirit. And I believe Nick is responsible for some of that too.
For what?
The version of this where you use the L2 norm. The ensemble Kalman inversion thing. But let's focus on DKL because, well, the idea of this came from, sampling. KL is what we look at when we do sampling. This problem seems similar enough, so maybe using the KL can achieve similar results. And so if we instead look at the second kind, is exactly the same objective function I just put on the right-hand side of the second kind equation. And well, I give the definition over here, the Kullback-Leibler divergence, which I understand to this audience is a bit useless, but is there anyways in case you want a reminder. I'm gonna be focusing on the first kind because that's what the preprint is about. You can imagine that 99% of what I'm going to say applies to the second kind as well. So what sort of assumptions do we need to make this work? The kernel K needs to be smooth and actually very smooth with derivatives that are very well behaved. Pi zero, sorry, I didn't mention what pi zero is. Pi zero is a reference measure that is picked by the user, meaning me or you if you want to implement this method. And alpha is a positive parameter. So it's just a regularization parameter. So pi zero also needs to be quite smooth and Lipschitz, like with very nice continuity properties. The measure of mu is a finite second moment. And then in terms of the second kind, we need the forcing term and the lambda to be positive. This is just for the experiments that I have. I think these are not necessary, but let's start. So how restrictive are these assumptions? The ones on pi0, not so much, because pi0 is something that we pick. Normally, to describe any property of the solution that we know in advance. For instance, we know that it's concentrated in 0, 1, then we're gonna pick a reference measure which enforces this constraint. So the assumptions on pi0 are not too strong in my opinion. Similarly, the fact that mu has finite second moment is pretty much asking that the samples that we observe have finite variance. So really, it doesn't seem too much to ask. The assumption that might seem very restrictive is the one on K, because we need these kernels to be very, very smooth. But actually, in the realm of integral equations, this is the most common situation. Because if you have kernels which are discontinuous or degenerate, then there are specific methods that work very well because you can just move back to a finite discrete space and apply them. So the problem really is when K is moved, you cannot invert the integral operator. So this is in terms of applications, this is where you need methods that are efficient and work well. So the workflow is the one that you probably imagine, given the title of the workshop. So we start from the functional, we derive the gradient flow, which gives us a PDE. We are lucky enough that this PDE is also nice, so we can immediately write down an SD whose law solves the PDE, and then we derive an interacting particle system, and finally you just discretize this in time and obtain a numerical scheme. So I'm going to go through all of those, but this is just to give the picture of what is going on, and it's the same sort of workflow that you would follow to derive many other methods based on gradient flows. So the first part is looking at the functional. So this is the functional for the first time. And well, the first thing to notice is because of the definition of the KL divergence, the first term, which is mu log mu, is irrelevant with respect to the minimization because mu is known. So we can get rid of that, which is what happens over here. The second thing is that we're going to add this parameter over here. So this is a strictly positive parameter, which is there because we need to make sure that the argument of that log is never 0. So it's there mostly to obtain theoretical results. In the numerical experiments, we do set eta to be 0, but we were not able to prove theoretical results for eta equal to 0. In particular, this guarantees that this functional is stable in a way that I will talk about in a second. So if we pick alpha and eta being strictly bigger than 0, eta is the parameter that I just discussed, and alpha is the regularization parameter, we can actually show that this functional is convex and coercive, which is enough to guarantee uniqueness of the minimizer. If you remove the eta, this is not true anymore. And if you remove the alpha, even less so. So it's really crucial that we say eta, well, eta, I have a feeling that you could prove it, but I don't know how. So that's the truth behind the presence of the eta over there. The alpha is really needed. If you set alpha equal to 0, we know that the minimizers are not unique. So this is basically to say, look, we came up with a functional to solve this problem. The problem is imposed, but the functional that we look at guarantees uniqueness, which means you already have a problem, like a well-posed problem. You're trying to find one minimizer, not many of them. So the next bit is clearly obtaining the gradient flow. The gradient flow requires a subdifferential. So this, I put the subdifferential over there. Roughly speaking, this is what you would expect, meaning that if this is the functional I want to minimize, then this term is very standard, is what we've heard about today already a couple of times. This is the Kn between pi and pi0. If I want the subdifferential, this is the gradient of the log ratio. So this bit was easy to obtain. The second bit is already not very different from what you would expect. because 1 over pi plus eta is the derivative of the log. And then this is the derivative with respect to x of the kernel itself. So it's basically just pushing derivatives into integrals because we assume that everything is very well behaved. Proving that this is a subdifferential is a different business. Is quite involved, but it requires fairly standard tools. It's just a bit long. So once you have the subdifferential, you can write down the Wasserstein gradient flow, which looks like that. If we didn't have, so if we were in a standard sampling setup, we wouldn't have the beta, the b eta, which I defined over here. So we would only have this quantity, which is the potential of pi 0, which is what we already heard about today, and then the diffusion term. So really the main difference in this gradient flow from the one that leads to Langevin is the presence of this b eta. However, we cannot immediately use the theory of Wasserstein gradient flows to guarantee convergence of this PDE. By convergence, I mean that if we find a solution pi t, we will minimize functional f. This is because f is not strongly geodesically convex. So, you know, those exponential convergence that has been obtained in many results I'm mentioning here, probably the most famous book on the subject, doesn't apply in this case. But we will show convergence through a different route. Okay, so the next step, as you probably all expected, is I have the PDE, I have identified the diffusion part and divergence part. I'm just going to write the S corresponding SD, in which the diffusion part is constant and the drift is exactly what you would expect. What is the special thing about this SD is that is what is normally referred to as Lekin-Vlasov or mean-fit SD. So the drift term has two components. This one is very standard, it's just the potential. We're pretty happy with that one. The second one involves lambda t, which is the law of the process at time t. This means that I cannot just discretize this straight away unless I know the law of the process at each time, which in most cases you won't know. So this is this is what leads to interesting interacting particle systems pretty much. If you didn't have this part over here, then you would just discretize these using your favorite discretization method and you would get a numerical scheme and you would be pretty much done. But because we have this one, we need to do something about it. Thanks to our assumption, we can actually show that this process is very well behaved. In particular, the presence of the eta over there is crucial to show that that b eta term is Lipschitz continuous. If you have Lipschitz continuity of your drift, the analysis of an SD becomes very, very simple. If you don't, it's way more involved, and I do not have the capacity to do that. So once we are happy with the fact that this b eta is Lipschitz continuous, you can show that the solution is unique, is a strong solution. So you are very confident that your SD makes sense. And we can also show what we couldn't show using the standard approach of Ambrosio. So we can actually show that the law of this SD converges to the minimizers of the functional that we define. We don't have the rate because we don't use this approach of using geodesically convex functionals, but we can still show it. And this is based on the results from this very nice paper, actually, in which they look at a particular type of functionals, which is a functional plus alpha KL, where the alpha KL is the regularization term, and they give conditions under which, if you take the gradient flow, you have convergence. And these conditions mostly have to do with some, with the properties of the reference measure that you pick, which is very nice because the reference measure is something that you pick, so you can make those conditions true and obtain your results. And clearly, this only works if alpha is strictly positive, because if alpha is 0, then I have no reference measure and I cannot apply these results. Okay. Now, I am aware that there are a lot of well, not a lot, but a not unique number of methods to approximate making the glass of SDs. I'm not going to claim that this is the most common one, but to me, it was always the most intuitive one, which is, well, in my drift, I have the law of the process itself at each time. I don't know that law, but if I take several copies of my SDs, I have an empirical measure which hopefully is close enough to the law. So that's exactly what this interacting particle system does. It is the same, considering capital N copies of the SDs that I described before, and then replacing the lambda over here with the corresponding empirical measure. This is quite common. We didn't come up with that. Has been done in the statistical physics literature for a very long time, and is actually motivated by the study of gases. And because of our assumptions and the fact that the drift is Lipschitz, there is a very nice property which holds, which is normally called propagation of chaos, which I simplified a bit over here. It basically says that if you pick the first particle of this interacting particle system, and well, one of these particles, but you imagine that they belong to an infinite dimensional particle system, so you let the number of particles go to infinity, then you converge to the true SD at the standard Monte Carlo rate, meaning 1/square root of n. Again, this is very well known, but up to very recently, only for Lipschitz continuous drifts. So, which is why we ended up with this setup. This has been extended as well recently, but I won't go into that. Under similar assumptions to what you would expect for a Langevin diffusion, you can actually show much more. You can show geometric ergodicity. So what this is the results in the paper, but just unpack it a little bit. If I consider the empirical measures associated with two different starting conditions, x1 and x2, then I can show that they converge to one another at a given rate. The rate is given by rho n over here. And this is for any finite n particle system. As soon as you let n go to infinity, the constant goes to plus infinity and the rate goes to 1. So this is not enough to say that the McKean glass of SD satisfies exponential ergodicity. This only works for your finite interacting particle system, which, after all, is all we care about because we want a numerical scheme that works well. So it was enough for us to be able to say this. We can even say that if you let the number of particles go to infinity, the empirical measure of the particle system does converge to the minimizer. So eventually, we came up with an interacting particle system which is able to approximate the minimizer of the functional we were interested in from the start. Now, the very last step, as you can probably imagine, is for now, I've been talking about an interacting particle system that behaves in continuous time. We cannot implement this in continuous time. We need a time discretization. We considered a tamed Euler-Maruyama discretization. The reason for the taming comes from the fact that we have the eta. If we set eta equal to 0, you can potentially have a drift which is not Lipschitz anymore. And so with the taming, we sort of stabilize the drift. If you are happy to take eta to be, I don't know, 0.01, then you can imagine a simple Euler-Maruyama will also do the trick. And exploiting, again, quite recent results, this was published only last year, I think, you can show convergence of your tamed Euler-Maruyama to the continuous time interacting particle system. Bear in mind that all the constants that I had in the previous slide depend on n. And what I have in this slide depends on t. So you cannot let time or the number of particles go to infinity and still have these results. They only hold when you stop the interacting particle system and you have a finite number of particles. So in terms of practicalities, what do you do when you want to implement this sort of thing? Well, if you're very interested in obtaining visual representations, you have a particle system, you can use kernel density estimation to obtain plots, which is what we do. But bear in mind that this works very, very badly when you are in dimension above 2. So it's nice for visualization purposes, but I wouldn't recommend it in terms of accuracy. Then Phi0 is a prior or a reference measure, which you can pretty much imagine is anything you want, which is very well behaved, and you will encode smoothness, support, second moments. Normally, we pick it to be a Gaussian with the right, I don't know, moment or concentration. Alpha is selected by cross-validation, and there is a lot of literature in doing this for these squares. You can translate the literature to this setup. Combining the results of propagation of chaos and time discretization, we can actually give explicit bounds on the error between your numerical scheme and the Kim-Vlasov SDE. So eventually you could use this, for example, to select the number of particles and discretization step, depending on your computational budget. Okay. I spoke way too fast, I think, but I do have a lot of experiments, and I have even additional slides in case I have more time. So the experiments are not here to show you we have the best method ever, but are here to show you what are the challenges with this sort of integral equations, also because I'm aware they're not the most used tool in statistics. They are very common in the applied maths literature. And I think there are opportunities for us to work on these sort of problems because they really want good methods to solve them. And I'm not fully satisfied with what we did. So if you can come up with better ideas, I'd be very interested in hearing them. So this is one example of the integral equation of the first kind. So this is the integral equation that we want to solve. You can tell that part of this project was done during lockdown because the first experiment we came up with is about incidence curves for epidemics. So in this case, what you observe is the number of hospitalizations over time. That would be mu. Decay is describing delay between getting infected and getting into the hospital. And what you actually want to know is how the infectious disease is. So what is the infection curve? So that would be our pi. And we compare with a couple of other options that you have in the literature. So the first one is the Richardson-Lucy algorithm, which I find is a very fancy name to say EM for Poisson data, where EM stands for expectation maximization. Why do we look at this one? Is because the EM for Poisson data is minimizing the Kullback-Leibler divergence without regularization. So it's only minimizing KL between the right-hand side and the left-hand side. So it should be quite close to what we do. SMC EMS is an SMC implementation of the EN with an additional smoothing set. And it will become apparent in a second why you need that. The right estimator is an estimator that was developed by, I think, a group at Apple to specifically solve this problem. So the problem of density or deconvolution for epidemiology. So why is this specific to this problem? Because in this case, the K is actually K of y minus x. So deconvolution, it normally refers to cases in which your kernel depends on the distance between y and x, but it's somewhat simple. It doesn't depend on more complicated physics structures than that. So this is simulated data. So I hope it's visible from the bottom of the room. The black line is the true incidence. The color curves are the three different methods, but the dotted gray line is EM. And it's quite clear that EM performs terribly on this task. And it sort of recovers the shape, but it's super spiky. You cannot rely on what EM returns. This is very well known, and it has to do with the fact that you observe samples from mu, so you observe a finite number of samples, but the parameter that you're trying to estimate is a continuous function pi. So the maximum likelihood estimator, which is what the EM is after, is not consistent, and so tends to basically concentrate on the observations that you have. So if you can see on this other plot, which is the crosses are what you observe from mu, and the curves are the recovered mu's once you have obtained pi. So you take your estimator of pi, you convolve it with k, and you obtain the recovered mu. EM is just basically fitting the crosses. Is some sort of fitting procedure for the crosses. So he's doing a very good job at recovering the reported cases, but a terrible job at estimating the incidence. So it is known for a while that you need to regularize these algorithms if you want to use them to minimize the KL. And well, the other three options, the red and green, are very, very close. This is not surprising because they're pretty much doing the same thing, minimizing the KL, plus some smoothing to avoid the problems that EM shows. And the right estimator is also doing a pretty good job because it's basically fine-tuned for this problem. We also look at what is the effect of the reference measure, because in SMC EMS, you don't really have the possibility to, there is no reference measure, so you don't really have the possibility of using prior information. You just take the outputs of EM and you smooth it out a little. And this is particularly evident when you think about misspecified models. So what do I mean with misspecified and well-specified? Well-specified, well, is pretty self-explanatory. The data are obtained by just delaying my incidence curve by k. In the misspecified case, this is noise by the fact that over weekends, the cases are reported late. So if you get detected on a Saturday, you might get reported on a Monday, which is quite fitting for the very first stages of the pandemic, in which this happened a lot. And well, runtime, of course, doesn't change because the reference measure doesn't change the runtime. The ISE is the integrated squared error, so I don't want to focus on the mean of my distribution. I really want to know if we can well approximate the whole shape, because when you think about integral equations, we want to recover the whole shape. We're not just interested in, I don't know, the tails or the center. We want to be good at recovering the whole distribution. And you can see that, well, when I look at the error in recovering pi, they are quite similar. I'm not including EM because it's just terrible at this job. But we do quite well, and we're better than the others, not by orders of magnitude, but I mean, acceptable results, I would say. This is a 1D problem, so somewhat very easy for discretization methods. If you look at a very, very simple problem, which is a mixture of Gaussians, which I want to deconvolve. So I'm looking again at convolution, so the K as this particular shape. I have X's, I add, which are Gaussians. I add some noise, which is also Gaussian. I observe the Y's, and I want to recover the density of the X's. So a super toy model. What I'm comparing here is what I just described with the one step late EM, which is a variant of EM in which you can actually add the penalty. So these two algorithms are minimizing the same exact functional. And I have dimension 1, 2, 3, and 4, because actually these integral equations mostly come in dimension 2 and 3. So they are not super high dimensional problems. They're already quite hard in dimension 2 and 3. And the gain in accuracy is quite evident when you get to dimension 3 and 4. This is because the one-step late EN is discretization based. You take the support, you discretize it, and then you try to solve. But if you fix the computational budget, Monte Carlo particle-based method will outperform pretty much any discretization method. If you instead compare with SNC EMS, which is also particle-based because it's a sequential Monte Carlo implementation, the difference is much smaller, even though this gradient flow one is slightly better. And I wasn't too upset about this because actually we proposed the other method as well. So, I mean, it would have been pretty sad to just see that the method that we proposed the year before was terrible. So to the second kind, these are very, very toy results, but just to show that this approach can be extended to other problems. We did the first kind, we're working on the second kind, but there are many other types of integral equations that you might want to solve. So this is to remind you what the second kind is. In this case, everything is very Gaussian. This is basically the invariant measure of an Orstein-Uhlenbeck process. And I'm comparing for lambda ranging from 0 to 1. As lambda goes to 1, the problem becomes harder to solve because the kernel K is less invertible. In this case, you have invertibility. It's a well-posed problem, the second kind. The first kind is not, but this one is. And I'm comparing the results with, so this dotted line is what we have in terms of integrated squared error. The other one is a reversible jump implementation of the von Neumann expansion, which is just a way to invert the kernel. And this is also not discretization based, it's based on MCMC, but struggles a lot because the von Neumann expansion struggles a lot when lambda gets close to 1. And yeah, the last one, this is a problem that we've been thinking about for a very long time, which is finding eigenfunctions of a given kernel. This is normally known as Caronin-Loew expansion when you think about GPs, but it's really just an eigenvalue problem. And I'm considering two types of K, one is normally known as squared exponential and exponential. This one does not fulfill our assumptions, but we're still quite robust in obtaining the result. So the black line is the analytic form. What we do is the dotted line, and the gray line is the Nystrom method, which is just a fancy way to say you discretize and solve an eigenvalue problem for a matrix instead of an integral kernel. So I mean, I'm not 100% satisfied with this, but considering that I obtained them last week, I'm pretty pleased for the moment. So I'm going to skip on this because I managed to talk for long enough about the experience. What was the motivation and what are the takeaways of this? Well, these problems are very, very studied in the applied maths literature, but normally they look at discretization type approaches. Based on basis functions, there are a ton of papers in which they slightly change the basis functions. You can use splines, you can use wavelets, you can use whatever you like. They obtain very good results in dimension 1, but in dimension 2, not so much. So also they require mu to be known analytically, which in the case of the epidemics model, you don't know the number of hospitalizations analytically, you just record it day by day. You can, of course, with a kernel density estimation, but then you add variability over variability. As I mentioned, they don't work very well for high dimension, and when they do, they require very specific kernels. So there are very fine-tuned approaches for, I don't know, image deblurring, which is a deconvolution problem. But when you try to apply them to something else, I don't know, recovering CT scans from the CT scan data, they just don't work because they are not built for that. And on the other hand, if you think about using gradient flows or any sort of Monte Carlo approach, discretization-wise, you have less problems because they are adaptive. The diffusion terms allows the particle to move around, so they move where is relevant. They cost less than standard discretization steps, and you can implement them when you only have samples from mu, which is nice because you don't need this additional layer of I need to build a functional representation of mu. And well, you can also improve things by using this reference measure, but some of the discretization methods allow that too. So yeah, that's all.
Very nice.
How much of this theory really relies on this being a kernel? Like, could you use other smooth functions as well?
What do you mean with?
So the K, let's take the sigmoid version of the first kind, right? You have this kernel K, you mentioned it's for that smooth and bound and all that. So let's say I have no problems with that, but I don't want to use a kernel. I want to use another function that has 2 arguments that's not a kernel, even though it's smooth and bound and all that.
For the first time, you really need to be a kernel, not because of the method itself, but because the equation is defined in that way.
Well, I mean for the method. So could you extend your method to problems that look exactly like this?
Yes.
Except the kernel is not kernel.
Yeah, I think so. For the second kind, for example, in the first kind, we also assumed that the kernel was Markov because we work in probability space and you want the 2 sides of being probabilities. For the second kind, it doesn't have to be Markov, so you can drop that very easily. I think you can drop a lot of the assumptions that we made. We made them to make our life a lot easier. But yeah, I think you can drop a few of them if you are happy to keep smoothness and regularity of the derivatives. Yes.
Yeah, I was wondering, did you in the experiments look at, so you mentioned there's this square root of n convergence rate expected, right? Monte Carlo rate. And so I haven't checked these papers very carefully, but there's been some recent work where the claim is that the convergence can be faster, this theoretical work. And it's just like, it's a little bit tangent, but would it be possible to observe this maybe? I don't know if it's true or.
I think it, so we observed it in a 1-dimensional example for small n. So if n is small, when you move from, I don't know, 50 to 100, the decay is very steep in improvement in error. But when n starts to get bigger, it sort of really follows 1 over square root of n. So when you can make big improvements when n is small, but if you are happy to go above, I don't know, you want 1 decays n about 1,000, you can really see that the decay is square root of n.
Okay.
But also didn't look into this like thoroughly. We just have one example in which we plot the error as the number of particles increases.
Thanks for a really interesting talk. I just wanted to check my understanding when you were saying that you can't invert the integral operator. So with my kernel hat on, I tend to think of things like if the kernel is characteristic, then it's injected onto its image and you can invert it. So when you said you can't invert the integral operator, did you really mean that you're in the misspecified setting where the data don't come from the image of the operator?
So yes and no. What I mean with that is that the problem is normally when you look at this sort of integral equations, the kernel K, you can think about it being a Gaussian. And if I look at it from a functional analysis point of view, the norm is not smaller than 1 and I cannot invert it. Like the inverse doesn't exist in the space of kernels, which pretty much means that if I try with a sort of pseudo inverse, I get no continuity with respect to the data, which is the biggest problem really over here. If I change mu a little bit, I cannot guarantee the solution that I obtain is going to change a little bit. It could be dramatically different.
But then I haven't understood, so I need to maybe grab you up to this.
Yeah, I have to say, I don't know I know this from the functional analysis point of view, but I'm not so well versed in the other kernels bit. So yeah, it would be great.
One small one about the taming scheme.
Mm-hmm.
Did you try without taming? And
Yes.
actually, was it unstable? And did taming solve the problem?
It depends a bit on your K. If your K is Gaussian, then you don't need taming, it works. But we also try with a gamma distribution, which doesn't fulfill our assumptions because the gradient at 0 is very unstable. In that case, it breaks.
So the normal one breaks, but taming did work.
Yes.
Okay. If no online questions as well, so there's now a tough break. Let's thank our speaker again. I am our last talk is going to be given by Xiang Liu. I'm very pleased to introduce him. He's at University of Texas. He's a professor at University of Texas, and you might you heard a lot about today in every single talk about SVGD. So he's one of the inventors of SVGD. So it's great to have him as a speaker. Jen, yours.
Okay, thank you so much. It's a great pleasure to talk here. So the topic today is going to be slightly different from the earlier talks on gradient flows. So this is really still about flow and diffusion processes, but more connected to optimal transport. I think ultimately that there are lots of intrinsic connections that I would like to explore. But this talk is more about generative models and optimal transport for data that is unknown and only observed through data distribution. So for supervised learning, really we can think about a unified framework as building transport maps between two empirically observed distributions. For example, when we build generative models, it's really about converting or transporting a noise distribution such as Gaussian to the data that we want, right? And more generally, we have domain transfer where we have observed two empirical distributions and want to build transport maps between these two distributions, right? Now, the key challenge here is that we don't actually observe matched pairs. We only observe two distributions, and there's no well-defined matching pre-hand that is given to us. So here's the formal definition. It's a kind of empirical version of transport mapping problem. So we are given two sets of observations, x1 and x2. They were drawn from two distributions, pi0 and pi1. And they were assumed to be unknown. So this is a statistical estimation problem in the sense that the data is not, the distribution is not observed. And then we want to find the transport map T that takes the sample from pi0 and transfer into pi1, right? So this is really, I think, is a very interesting problem because it really combines a statistical component where we don't know the two distributions. And then that's also a computational component here because we are given two distributions. Calculating the transport mapping is a highly non-trivial problem, right? Like the gradient flow and sampling is kind of trying to calculate a transport mapping between two distributions. So there has been lots of works, and based on the different types of the transport mapping, we can have either one class, one step or static models, where we just build a neural network to model the transport mapping, right? But recently there has been network work on building T implicitly as a continuous time process, right? So this could be either a differential equation or a flow model, or it could be a stochastic differential equation, in which case it's a diffusion process. So in this case, we basically start from T equal to 0, starting from a sample from pi0, and we want to build a process that transfer the sample to a sample of pi1 at the time T equal to 1, right? Now the idea is that it turns out if you want to directly build the mapping, it's pretty difficult. So you can write down, let's say, optimal transport formulations, and then you will get some optimization problem. And typically, because that optimization is constraint optimization, typically you will end up with some minimax problem. And that is quite difficult to solve, unstable, very difficult to scale. But it turns out if you now seek to find a continuous time process, this is really the dynamic formulation of optimal transport, then the problem is actually easier. You can actually write down pretty nice and simple objective function for this continuous time process. So the training is easier, but then the inference is slower because at the inference time, you are actually you need to run the whole continuous time process rather than just applying a well-defined map, right? So that's a trade-off between the training and the testing for the one-step model versus continuous time models. And one question is, how could you bridge the gap? Could you find something that is both easy to train and faster to inference? So this is now. Here is one concept that I want to clarify, which is in machine learning, especially for generative models, we really are interested in finding an arbitrary transport mapping. So any mapping from pi0 to pi1 is okay for our purpose in theory. But given two distributions, there are actually infinite number of transport mappings. And we have been talking about, there has been lots of discussions on, what specific transport mapping you're interested in. In that case, we have this notion of optimal transport, which is trying to identify a special transport map that minimizes certain cost of function. So this is a typical formulation where C here is a convex cost function. It could be L2 or L1. You want to find the coupling to minimize the cost. And equivalently, you can write down this optimal transport as in a continuous time way. And now this directly reduces to optimizing a continuous time process, right? But then the problem is that solving the optimal transport could be unnecessarily difficult because we don't actually need to find the optimal transport for problems like generative models, right? So then, then what would be a nice notion that is easier to calculate, but still very useful for the purpose of generative models? And it turns out that's this notion of street transport that is really natural for this setting. So the idea is that when you want to build a continuous time transport mapping from two distributions, right? In computer, in the end, at the inference time, we need to actually simulate this process. And the simplest simulation is simply discretize it using Euler scheme, right? Now we hope that discretization can be done, when a small number of steps is possible, or when a large step size, right? And now the question is when this will happen. Well, it turns out if you think about a differential equation, ODE process, right? So the case when it's trivial to solve is when the trajectory of your dynamic system is always a straight line. It's a straight trajectory, right? So here on the left, if you have a curved trajectory, then you are going, when you discretize it, you will have error, right? And that's not ideal. But then if your trajectory is straight, then you can simulate when in one single step, and that's ideal case, right? And this is a kind of notion that I think is very relevant for computation, for machine learning applications, because we want our system to be computationally efficient, right? So it turns out that you can build a theory about this street transport, which is the transport mapping that can be induced by ODEs that follow straight trajectories. And it turns out optimal transport mapping always follows straight trajectories, which is kind of obvious, but the opposite is not necessarily true. And in this talk, we are actually going to propose a method to find straight transport mappings. And we will show that the method can also be extended, can modify it to find optimal transport. So this is the main idea of the method. It's called rectified flow. So it's a way to build a differential equation, but it can be easily extended to diffusion processes between two empirically observed distributions in a way that it tries to follow straight trajectories as much as possible. And we have this iterative process that, once you build one flow, you can actually iteratively refine it so that you can straighten its trajectory. And if you repeat this process, theoretically, you will end up with a straight coupling, straight trajectory. But if you do certain modification, it turns out you can also use it to solve optimal transport. And the idea is that, unfortunately, I don't. This is a video, but unfortunately, it's not showing. But the idea is that when your trajectory are not straight, you may have these crossings of the trajectories, and the idea is to iteratively revise the crossings so that you can get the particles doesn't collapse as they move. But let me talk about this in detail later. Okay, so but here's the key idea. It's actually a very simple idea. So let me set up the things. So now assuming you are observing a sample x0 and x1 from pi0 and pi1. Remember, pi0 and pi1 are unknown, so you draw samples from them, right? And then once you draw samples, now assuming these samples can be arbitrarily dependent. Now assume, for example, they are independent, right? Then you connect these two samples together. So you will get a straight line connecting them. You will get linear interpolation between x0 and x1. And then if you are interested in finding an ODE, differential equation, for connecting the two distributions, in certain sense, this is already something that you can work with, because if you take the gradient for linear interpolation, you will actually get an ODE. So the ODE says that the derivative of xt equals to x1 minus x0, the final point minus the starting point, right? But then this is obviously a trivial ODE in the sense that it's not simulatable forward in time, or it's not a causal system, because in order to calculate xt, the derivative of xt, you actually need to know x1, right? But then if you already know x1, there's no point to simulate, right? So it's a trivial system. But then the idea is that what I can do is I can try to causalize it, meaning that I can try to learn an ODE to imitate this non-causal process as much as possible, right? So here in this plot, I kind of show the idea. The purple point is pi0, the red points are pi1, and then here you just randomly draw samples from pi0 and pi1. You just connect them with the straight lines, right? Now you can sort of see that you get a bunch of random trajectories, linear trajectories, right? Because they are random, like the coupling between x0 and x1 is purely random, so you have these crossings sometimes, and this is it. This is where the problem comes from, because whenever you have a crossing, you have two potential directions to go, and it's unclear which one you will go. And this is what makes the system non-causal. And this is the thing that we need to fix to make it causal. Okay, so here's the way we fix. It's very simple, surprisingly simple. So you basically just find the ODE system, which has a velocity field v. Now we assume v is a neural network. We are going to optimize it by minimizing the difference between the straight line directions, which is x0 minus x1 minus x0, wins the velocity field, right? So basically you're just trying to match the velocity field of your causal system with this the velocity field of these straight trajectories, right? Now, if you work out this thing, it's very simple. And you can show that, in fact, that the exact optimal velocity field is simply the conditional expectation of the directions. So basically what's happening is, let's say, look at the left figure, you have a bunch of linear trajectories. These trajectories cannot be the solution of any differential equation because there are trajectories that are intersections. Whenever there are intersections, it's impossible to be the solution of ODE because ODE by definition only has one direction. And then you causalize it, you get this V. Now what's happening is that whenever there's a crossing point, you are going to just take the conditional expectation. You will see that, given any point xt, right, you will look at all the trajectories, linear trajectories that pass that point, and you will take the average of the trajectories, conditional average of the direction of these trajectories. And then you will get velocity field. Now, if you simulate that velocity field, what's happening is that you are going to basically imitate all the local behaviors, right? If you look at these two curves, now after you simulate the velocity using ODE, you can sort of see that you basically follow the basic pattern, but whenever that's a crossing term, the ODE is going to travel in a way that avoids the crossings, right? In this case, the particles from the above is going to be bounced back to the upper part, right? So in the end, you will get a non-crossing trajectory. Now this is the OD that we learned from by causalizing the linear system, the straight lines, right? Now what's nice is that once you learn this, you actually get a transform mapping from pi 0 to pi 1. And what we are doing is only solving a least square regression problem, right? So this is the key point, as I said, as I just mentioned. So basically, we are just it's an iterative rewriting process. Basically, we connect the dots with certain interpretation, and then we convert the interpretation process into a causal ODE system. In that way, you still preserve the marginal distributions along the way. I will talk about that. But you are building a simulatable transport mapping, right? And then what's nice is that you can actually repeat this process. So after you get your differential equation, you can simulate your differential equation from any x0 to the final point x1, right? So, and now you get a new set of couplings, right? You get a starting point and the end point from the ODE system. You can sort of see that the coupling you get now is actually better than the original coupling. So the original coupling is purely random, it's independent coupling. But now because the ODE system tries to avoid the crossing, so because of this, the coupling induced by the ODE system is actually a better coupling. Better in the sense that it will actually minimize, it will actually has lower transport cost for any convex cost function. I will talk about this later. And then so what we can do is we can start from this new coupling and connect them using linear interpolation again, and then run and then try to get a causalized flow again. So this process is called reflow. And in this case, if we actually reflow, what's happening is that we will connect these points with the linear trajectory, right? And then we'll reflow it, because in this case, there may not be lots of conflictions. As you reflow it, you may get an ODE system that exactly follows the original linear interpolation. And as a consequence, in this case, you get a straight trajectory. You get an ODE with a straight trajectory. And this is really nice, because then you only need to simulate for one step. So this is the overall algorithm. So we start from any coupling. So this is actually a coupling optimization algorithm. It's actually you start from any coupling, In practice, we can start from independent coupling because that's something that is easy to construct just from empirical observations. But you can start from any coupling in theory. And then what you can do is you use the reflow procedure. You train a velocity field that causalizes the linear interpolation of the coupling. Now you get a dynamic system or a flow model. And then you use an ODE solver to simulate your flow, and you will get a new coupling by taking the starting and end point of your ODE system. And this is a new coupling, and then you repeat, right? And it turns out this process is actually iteratively improve the quality of your coupling, both in terms of optimal transport cost and in terms of the trajectory of the straightness of the trajectory. In theory, if you repeat this process, in the end you will get straight trajectories. But in practice, we find that often you get straight trajectories just within one or very pretty straight trajectories wins one or two reflow steps. This is an example, empirical example. So we are using this algorithm for generative model. So we start from Gaussian noise and generate some cat image, right? So the first row here is the flow that we obtained from independent couplings. So in this case, because the couplings are independent, causalizing it would cause crossings. So the trajectory of the system is not straight. And you can sort of see that. So here, N is the different number of discretization steps, right? So if we use N equal to 1, which is just simulating the whole ODE system with one Euler step, which is obviously not ideal, you can sort of see that we don't get really nice images. As we increase the discretization step, you get better images. But you also get different images. And the reason is because the trajectory is curved. So when you use different discretization steps, you will end up with different places because you're making different mistakes, right? And then for the second, now what we can do is we can take the coupling from the first flow and then reflow it again to get another ODE that has a straighter trajectories. And in this case, you can sort of say just within one reflow step, you can get pretty straight trajectories because even if we use just discretize the whole system with a single Euler step, you already get pretty good result. And in fact, if you discretize it with different steps, you get the same result. And this is an indication that the system follows pretty straight trajectories, right? Now the bottom two rows are the same thing, but we are using the same algorithm for transport mapping. So here we take a human face and we transfer it into a cat face, and the same thing happens. So for the first flow, it's not quite straight, so you get different results from different discretization steps. But the second flow is very straight, so it's robust to the number of steps of the discretization. So we actually scaled this method up to stable diffusions, and they also get pretty good results, but reduce the computation dramatically. So the idea here is that in text-to-image generation, we are building generative models for images, right? But we are conditioning on the text, right? So we take a text prompt, right, and generate images. Now we can modify our method easily just by conditioning the velocity field to the text prompt. So your velocity field now is going to be a neural network that takes both your xt and time t as well as a text prompt as input and output the update direction, right? And because of the computational cost, we actually, instead of using independent coupling as a starting point, we actually use the couplings induced by stable diffusion as the starting point. So what we do is we take some random prompt and take some random noise, x0, and use as stable diffusion to simulate a final image x1, right? Now we get lots of triplets of prompt, noise, and images, right? And we can use these triplets to train a flow, a new rectified flow using the auxiliary function here. And once we trained, we get a model that is pretty straight. But because this is a very large scale model, we actually further improve the result by further refine the flow to distill it to a one-step model. And then as a consequence, we actually get pretty good results. Get comparable results in terms of image quality compared to Stable Diffusion, but improve both the training and the testing cost dramatically. And you can sort of see from here that after we apply the reflow, we can sort of see the image quality improves dramatically for small number of steps, right? And this is expected because the trajectory of the model is straightened. Okay, so any question at this point?
Yeah.
Maybe just one quick question.
I don't think. Can you hear Tobias?
Yes. Yes.
One thing that was not quite clear to me is: do you start with a diffusion model that you then rectify and distill, or can you train the generative model from scratch without any base model?
So the generative model is just the flow model, right? What do you mean by training a generative model from scratch? Because okay, so
if you can use that loss to train the full generative model, or if you start with the diffusion model and you use rectified flow to improve it. Sorry.
We can do it either way, right? We can do it either way. So you can start from diffusion model. They are actually not diffusion models because in the end you will convert the diffusion model into a flow model. So you start from flow model, you get the couplings, and then you use the coupling to train another flow that has straighter trajectories, right? Or you can just take your original data. So let's say you have a set of images. You just take your original images, and then you randomly pair each image with a random Gaussian noise, and you connect them with linear straight trajectories, and then you can train it with rectified flow. You can train it either directly from the data or from the result of any other model. Yeah.
There is an online question. How do you actually distill the model into a one-step model?
Yeah, so that's actually a simple step. Let me actually. So what's happening is you have an ODE system, right? Differential equation. What we do is simply simulate the ODE system. Now we get a coupling from x0 and x1, right? And then, if we are doing reflow, we are going to use this procedure, the loss function that we have here, to calculate another flow that has straighter trajectory. But then if we want to distill, we simply just train a neural network that takes x0 as input and the output x1. So we are simply using a neural network to approximate the mapping of the differential equation from time 0 to time 1. And that's the final step. In principle, what's happening in this algorithm is that we start from the independent coupling, and we use the reflow to improve the coupling for a number of steps. And in this case, we just improve it for one step. And then finally, at the final step, we take the ODE, and we train another model to distill it into a one-step model. So the final step is trying to approximate the original ODE without actually trying to improve it. Is it clear?
Yeah, thank you.
Okay, sounds great. Okay, so I can now just talk about some of the theoretical guarantees for this method. So one important property of this method is that it preserves the marginal distribution, and this is very important. So what's happening is that you have this xt, which is the linear interpolation process, and then you have the zt, which is the trajectory from the ODE, right? And obviously these two processes are different. Both of them are random process because I'm having a random starting point and ending point, but they're constructed in different way, right? xt is a linear interpolation process, given x0 and x1, right? Now zt is a causal ODE system. But then turns out the marginal distribution of these two processes are always the same, even though the joint distribution is not the same. And because of this, we can claim that the coupling induced by the ODE is actually the right coupling for pi 0 and pi 1, right? For the intuition, we can sort of think about this as, in a physical way. If you take a small volume in the space-time, and then you watch the flow that comes into the volume and going out of the volume at every time, then you can sort of see that even though these two processes have the direction of the flow can be very different, because you are kind of rewiring the trajectories, but the number of flows that in and out are the same. So that's why overall the evolution equation is the same. So this is kind of physical intuition of why this is true. But then mathematically, that's a very nice result here that shows the connection with the continuity equation. So basically, if you derive the continuity equation for both xt and zt, you get the same continuity equation, and that's why you get the same marginal distributions. And the general result here is the following, which I think is very interesting. It's close to what I think many people knows, but is a generalization. So basically, you take any arbitrary stochastic process xt with a smooth trajectories, and then you can define this expected velocity. The expected velocity is that you condition any point, and then you watch all the trajectories that pass that point, and then you average over the derivatives of all the trajectories that passing that point. And this gives you a kind of expected velocity. And then it turns out the marginal distribution of the xt only depends on the expected velocity. It doesn't depend only on anything else about random process. And it follows this continuity equation, classical continuity equation, given this velocity. Yeah, and you can it's trivial to show that xt and zt actually share the same expected velocity, and this is why they have the same marginal distribution. And then another very surprising property is that as you reflow, you are guaranteed to decrease all convex transport cost. So here C is any convex function, and then basically the coupling induced from the ODE, which is Z0 and Z1, always have small or less or equal transport cost than the original coupling, as you are doing the reflow, right? The intuition, I think, from here is very simple. It's basically triangle inequality if you want to prove it for L1 cost. But this actually applies to any convex cost. And it's not surprising that what you can do is you can just apply a bunch of Jensen's inequality in this case, in using the marginal preserving property in certain ways. You can get a pretty straightforward proof. And then we also show that if you apply this reflow process for infinite number of steps, then your trajectory will be eventually straight, right? This is a relatively weak result. I think in terms of convergence, this should be improved. So basically, you can define this notion of straightness, which is simply the trajectory, the variance of your velocity direction along the trajectory. So if s equal to 0, it means straight. And then you can show that as we apply this reflow process, you can get the maximum straightness in the first k step decays over 1 So this is actually very similar to the analysis of gradient flow. So so it turns out in the analysis, this SZ is exactly certain notion of gradient. And then that's why you can use telescoping sum to prove this kind of result that is really similar to the bound of gradient norm in gradient flow. So certainly that's certain gradient flow underlying here. But this process is actually discrete, so it's so it should be possible to derive a continuous time version of this. Okay, so I also mentioned about this street coupling, this concept of street coupling. The street coupling is any coupling which can be connected, which can be derived from an ODE process that follows street trajectories, right? Or you can define it as the fixed point of this rectified process. So it turns out in one-dimensional case, one dimension is very special. So the street coupling is actually equivalent to optimum coupling. In fact, when you talk about optimum coupling, you have to fix the cost function C, right? So in one-dimensional case, all the optimal coupling actually coincides. You have one unique optimal coupling, which is the monotonic coupling. But in higher dimension, different cost is going to give you different optimal coupling. So in this case, street coupling is a superset of optimal coupling. And here's an example. You have on the left you have an optimal coupling. On the right you have a street coupling, which is optimal coupling, but you apply certain rotation operators, and the rotation doesn't break the intersection property. So this is kind of, and I think here, the essential difference, I think, between street coupling and the optimum coupling is that in street coupling, you have certain rotation component that is not removed. Now, if you remove that rotation component, you can actually get optimal coupling. And this is what you can do. For example, let's see if you are interested in just solving this L2 optimal coupling, optimal transport. You want to minimize the L2 norm square. What you can do is you can modify the method slightly. So instead of just finding an arbitrary velocity field V, you actually constrain your velocity field to be a gradient field. So now you are just assuming your ODE is a gradient flow. Well, but it's a time-dependent gradient flow, right? And then you find the F by minimizing exactly the same loss function, except now your velocity field is the gradient field of F, and you're optimizing F, right? It turns out if you replace this with the reflow, and then you repeat the reflow for a number of times, you will converge to the optimal L2 optimal transport mapping. And the intuition is that it turns out you can take any velocity field that you can decompose it into a gradient field and the rotation component. And when you solve this optimization by constraining the velocity field to be F, you are actually conducting this kind of decomposition, and you kind of remove the rotation field and just get a gradient field. And then you can actually extend this idea to any other transport mapping as well, and any other cost function as well. And you just need to modify your ODE so that you apply another monotonic mapping, which is the gradient of conjugate of F of C. And then you need to use this this conjugate, this fragment divergence like loss function other than the L2 loss. And if you do this, you're actually solving the optimal transport for general convex function. Yeah, and then okay, so and then it turns out this framework is also more general in the sense that you can replace the linear interpolation with any arbitrary smooth interpolation, and that actually allows us to derive many existing algorithms such as DDIM and probability flow ODEs from the score-based method as special cases. It turns out you can interpret these methods as using special kind of trajectories that is not necessarily strict. It turns out you can also extend this idea to diffusion processes. And what you can do is instead of taking linear interpolation, deterministic interpolation, or smooth interpolation, you can actually take Ito interpolation, and you can, in particular, you can build a Brownian bridge, for example, and then you can use the velocity, expected velocity field from the Brownian bridge to approximate to learn your model. So this is a kind of allows us to kind of generalize this whole idea to taking an arbitrary path and do it. So I don't think I have enough time for this. So I think I will just go very briefly here. So basically, this is the same kind of the generalization to diffusion processes, but then you can cook up the general concept of Markovization. So the transform mapping from xt to zt, it actually can be interpreted as a process of Markovizing the linear interpolation process. So yeah, then you can use this to construct the different diffusion processes. So I think I will just stop here and maybe take questions. Thank you.
Yes. Questions? I can use my phone as a microphone. So I have some question. I can start maybe about there are two questions really relate to each other. When you optimize it, you take one step. How do you choose the step size and what changes with respect to that step size? So when you when you distill it, I guess it all boils down to one step, and then I guess you need to still choose the step size.
Okay, so we actually, every time we actually solve this optimization fully. So we just don't take one step. We actually just solve the whole optimization process.
Okay. Okay.
Yeah.
But
yeah.
then
So yeah.
But then you also said you don't want to iterate this many times because then it actually stops working. Or is that true?
Yeah, yeah. So we actually we just repeat the whole process for one time. So we take random independent coupling, and we train a model, a V, from that, and we simulate the flow from that V. So we get a new coupling, and then we apply a wave flow on the new coupling again, and that allows us to get straight trajectories. So it's here. So basically, one step in the sense that we do one step of wave flow.
Okay. Any other question? No? Okay, let's thank the speaker again then. Thanks a lot.
Thank you.
All right, you can unshare. I guess we will just conclude. If you wish to leave, it's fine as well. What do I do? I can share this screen. Am I sharing this? Okay, so this was okay. So it's time to say goodbye. Very sad, but also very tired. I think there's not a lot of oxygen here as well. So yes, yeah, this was great. Thanks for all coming. Thanks to the organizers. It's not just me. There's Chris, you have seen. Louis was not here today. Theodore was here, he left. Yeah, there's nothing else to say. Thanks to the RSS team and RSS in general to sort of provide the venue and all that and the organizing this. And thank you for coming and see you later at some point.